We feel its pull every second of every day. It's an invisible force that tethers us, our cities, our oceans, and our atmosphere to this giant, spinning ball of rock. We call it gravity, and it exists because the Earth has mass. An almost unimaginable amount of it, nearly 6 sextillion kilograms, an anchor for everything we know. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if that anchor, the very stuff creating that force, is secretly changing? What if I told you that right now, Earth is in a cosmic tug of war, gaining and losing tens of thousands of tons of material every year? This is the story of Earth's mass, a number we take for granted, and the mind-bending question of whether our planet is, on the whole, getting heavier or lighter. The answer might surprise you. The invisible anchor. What is mass? Before we can figure out if the Earth is gaining or losing weight, we have to get straight on what mass actually is. It's a word we use all the time, but it's one of the most misunderstood ideas in all of physics. Picture this. You're standing in a room, holding a single feather in one hand and a heavy bowling ball in the other. Now, push them both forward with the exact same amount of oomph. The feather darts across the room. The bowling ball barely budges. That stubbornness, that refusal to get a move on? That's mass. The bowling ball has more of it, so it digs in its heels and resists changing its motion. When physicists talk about mass, they aren't talking about size or even weight. They're talking about the amount of stuff something is made of, the raw quantity of matter, the number of atoms packed inside. This stuff gives an object two fundamental properties. The first is asterisk inertia. That's our feather and bowling ball. It's an object's built-in resistance to being sped up or slowed down. Think about being in a car when someone slams on the brakes. Your body lurches forward because your mass is fighting that sudden change in motion. It wants to keep going. This is a perfect example of Newton's second law, the famous equation F equals ma. To get something to accelerate, you need to apply force. The more mass it has, the more force you need. A pickup truck needs a powerful engine. A bicycle just needs a gentle push. That's inertia in action. The second property of mass is its asterisk gravity pulling power. Mass creates gravity. The immense mass of the Earth is what generates the field that pulls an apple from a tree and keeps our moon trapped in a perpetual, elegant fall around our planet. Every object with mass exerts a gravitational pull on every other object. You have mass, so you are gravitationally attracting the phone in your hand, the walls of your room, and even distant stars. Of course, your mass is so tiny compared to the Earth's that this force is completely unnoticeable. But it's there. This brings us to the biggest point of confusion: the difference between mass and weight. In everyday language, we use them interchangeably, but in physics, they're worlds apart. Mass is the amount of stuff in you. It's constant. Your body has the exact same mass whether you're on Earth, on the moon, or floating in space. Weight, on the other hand, is the force of gravity pulling on your mass. Your weight changes depending on where you are. The moon is much less massive than Earth, so its gravitational pull is only about 1/6 as strong. You'd weigh 1/6 as much, but the amount of stuff making you wouldn't have changed at all. When astronauts float weightlessly on the International Space Station, they haven't lost their mass. They are simply in a state of continuous freefall around the Earth, so they don't feel the effects of weight. So, why do we care so much about this specific number, 5,972 sextillion kilograms? Because Earth's mass dictates almost everything about our world. It determines the strength of gravity holding our atmosphere in place, preventing it from being blown away by the solar wind. It governs the precise orbits of our satellites, which are critical for GPS and communications. Even tiny variations in the gravitational field, caused by an uneven spread of mass, help geologists probe the structure of our planet's core. Knowing this number with pinpoint accuracy is fundamental. So, is this number, this bedrock of our world, actually static? Or is it shifting, right now, as we speak? To find out, we first have to understand how we even managed to weigh something so impossibly large in the first place. Measuring the immeasurable. How we weighed the Earth. So, how do you weigh a planet? You can't exactly put it on a cosmic bathroom scale. This question puzzled scientists for centuries. The first real attempt didn't involve weighing the Earth at all, it involved measuring its pull. In the 1770s, a team of scientists in Scotland embarked on what became known as the Schiehallion experiment. Their idea was beautiful in its simplicity. A pendulum, when it hangs, points straight down toward the center of Earth's mass. But, they figured, if you hang a pendulum next to a huge object like a mountain, the mountain's own gravity should tug the pendulum ever so slightly to the side. They chose the mountain of Schiehallion for its nicely symmetrical shape. For months, in brutal conditions, they took painstaking measurements. They found that the plumb line their pendulum was indeed deflected toward the mountain. By surveying the mountain to estimate its mass, they could compare the tiny pull of the mountain to the enormous pull of the entire planet. Their final calculation was a bit off, but for the first time, humanity had a real, evidence-based number for the mass of our planet. They had proved it was possible. The real breakthrough, however, came in 1798, with one of the most delicate experiments in history, run by the English scientist Henry Cavendish. His main goal was to measure g, the gravitational constant, the universal number in Newton's equation that sets the strength of gravity itself. He knew that if he could find g, anyone could then calculate the mass of the Earth. His setup was a masterpiece. He built what's called a torsion balance, a wooden rod with two small lead balls, suspended from a wire. He then brought two much larger lead balls close to the small ones. The gravitational attraction between the balls, though unbelievably faint, caused the rod to twist. By measuring that tiny twist, Cavendish could calculate the exact force of gravity between them. Since he knew the masses of the balls and the distance between them, the only unknown left in Newton's equation was g. He had measured the force of gravity in a shed. Once g was known, the rest was simple math. Using the known radius of the Earth and the acceleration of gravity at the surface, 8 meters per square second, he plugged the numbers into Newton's law and calculated the mass of the Earth to within 1% of the value we use today. Today, our methods are far more advanced, but they use the same principles. Instead of mountains, we use satellites. Scientists bounce lasers off dedicated satellites, which are basically giant, cosmic disco balls covered in reflectors to track their orbits down to the millimeter. Any tiny wobble in their path reveals variations in Earth's gravity, allowing us to create an incredibly detailed map of the planet's mass. From a Scottish mountain to a laser-tracked satellite, the quest to weigh the Earth has been a story of ever-increasing precision. But all these measurements assume the mass is constant. Now, let's see what happens when we challenge that assumption. The cosmic diet. What Earth is losing. Our planet feels like a closed system, sealed inside its atmospheric bubble. But that's an illusion. Earth is constantly interacting with the harsh environment of space, and just like a leaky bucket, it's always losing mass. There are a few key culprits. The single biggest loss comes from atmospheric escape. Our atmosphere isn't held in by a lid, it's held by gravity. The higher you go, the thinner it gets, until it just fades away into space. In the upper layers, the exosphere, the lightest gases hydrogen and helium are vulnerable. A particle of hydrogen, energized by the sun, can get an extra kick from the solar wind. If that kick is big enough, the particle can reach escape velocity about 11.2 kilometers per second and break free from Earth's gravity forever. It's not an explosion, but a slow, steady hiss of gas leaving our planet. Scientists estimate that about 3 kilograms of hydrogen escape every single second. Over a year, that adds up to about 95,000 metric tons of hydrogen lost for good. Helium, which is a bit heavier, escapes more slowly, at a rate of about 1,600 tons per year. Together, this invisible outgassing is the main way our planet sheds mass. The second source of mass loss comes from deep within the Earth's core, thanks to Einstein's famous equation, E equals mc squared. This tells us that mass and energy are two sides of the same coin. Deep inside the Earth, radioactive elements like uranium and thorium are constantly decaying, releasing bursts of energy as heat. This process is what keeps the Earth's core molten. But here's the trick. When an atom decays, the total mass of the resulting particles is slightly less than the original atom. A tiny bit of mass has been converted directly into heat energy, which eventually radiates out into space. Because that energy has left the system, its equivalent mass is also gone. This is a much smaller effect, accounting for only about 1 ton of mass loss per year, but it's another entry on the loss side of the ledger. Finally, there's a more modern source of mass loss: us. Since the space age began, we've been launching rockets off the planet. Every time we send a probe to Mars, Jupiter, or out of the solar system like the Voyager probes, we are literally subtracting mass from Earth. This adds up to around 65 tons per year, though it fluctuates with our deep space ambitions. So let's tally it up. We have about 96,600 tons from atmospheric escape, a tiny 1 ton from radioactive decay, and another 65 tons from departing spacecraft. All told, Earth loses roughly 97,000 tons of mass per year. That sounds like a lot. But to know if the planet is truly getting lighter, we have to look at the other side of the scale. The space dust buffet. What Earth is gaining. While our planet is constantly leaking gas into the void, it's also being relentlessly bombarded by material from space. It turns out space isn't so empty, it's dusty. The inner solar system is filled with a fine haze of particles left over from asteroid collisions and the trails of comets. As Earth plows through this cloud, it acts like a giant cosmic vacuum cleaner. The vast majority of this material is in the form of tiny micrometeoroids, often no bigger than a grain of sand. They hit our upper atmosphere at incredible speeds and burn up in a fiery streak. We see these as shooting stars, or meteors, the visible sign of our planet gaining mass. When these particles vaporize, they don't just disappear. Their atoms iron, silicon, oxygen disperse in the atmosphere and slowly settle down to the surface, a constant, gentle rain of cosmic ash. How much does this add up to? Scientific estimates vary widely, but a commonly cited figure is that Earth gains somewhere around 40,000 metric tons of material from cosmic dust each year. That's like the mass of 4 Eiffel Towers raining down on us, pulverized into an invisible dust. This is by far the biggest factor on the gain side of the equation. It's also important to remember that when we build skyscrapers or when the world's population increases, we aren't adding mass to the Earth. All the materials for our buildings and all the atoms for our bodies are just being rearranged from stuff that was already here. The only way to truly add mass is to bring it in from space. So now, we have the numbers for both sides of the cosmic ledger. On one side, a gain of about 40,000 tons per year from cosmic dust. On the other, a loss of about 97,000 tons per year from escaping gases and other minor sources. The stage is set for the final verdict. We've checked the physics, we've weighed the mountains, and we've counted the atoms. We have the gains, and we have the losses. The final answer is just moments away. But first, if you're enjoying this deep dive into the hidden mechanics of our world, take a second to hit that subscribe button. It's a zero-mass action that has a significant impact on our channel. The final verdict. The moment of truth has arrived. Let's put the numbers side by side. In the gain column, we have the relentless influx of cosmic dust, adding approximately 40,000 metric tons to Earth's mass each year. In the loss column, we have atmospheric escape getting rid of about 97,000 tons annually. When you do the final math, a gain of 40,000 tons minus a loss of 97,000 tons, you're left with a net change of negative 57,000 tons. The answer is in. The Earth is getting lighter. Every year, our planet loses a net total of over 50,000 metric tons. The slow, invisible hiss of hydrogen escaping from the top of our atmosphere simply outweighs the constant rain of dust from space. Our planet is on a diet, shedding roughly the mass of a modern aircraft carrier every single year. Now, before you worry that gravity will weaken and we'll all float away, let's put that number in perspective. 50,000 tons sounds enormous, but the Earth's total mass is nearly 6 sextillion tons. The amount of mass our planet loses each year is a fantastically tiny fraction of its total, about 0.00000000000000001%. At this rate, it would take many millions of times the current age of the universe for the Earth to vanish. The effect is completely negligible. It won't change our gravity, our orbit, or our daily lives. But the fact that it's happening at all is what's so profound. It shatters the image of our planet as a static, isolated rock. It reveals Earth as a dynamic body, breathing in the dust of the cosmos and exhaling its own atmosphere into the void. The invisible anchor that holds us here isn't fixed. It's changing, constantly, in a delicate balance between its own gravity and the endless dance with its cosmic neighborhood. The ground beneath our feet may feel solid, but our planet is on a journey, and on that journey, it is, ever so slightly, lightening its load. The eccentric genius who weighed the Earth with 2 lead balls in 1798, one of the strangest, wealthiest, and most secretive scientists who ever lived, set out to do something that sounded like pure madness: to weigh the entire world. He wasn't a king with a massive army or a philosopher with some universe-spanning theory. He was a man named Henry Cavendish, a recluse so painfully shy he actually built a separate staircase in his own house just to avoid his housekeeper. And this man, working all alone, used little more than 2 lead balls and a wire to conduct one of the most profound experiments in the history of science. What he found wasn't just the mass of our planet, but a hidden number, a fundamental constant of the universe that dictates the invisible force holding everything together, from the moons orbiting Jupiter to the very ground under our feet. This is the story of how an eccentric genius managed to measure the unmeasurable and, in the process, gave us the weight of the world. For thousands of years, people had gazed at the stars and wondered about our place in the cosmos. We knew the Earth was big, but we had no idea how big. How much did it all weigh? The mountains, the oceans, the continents. Everything. It's a question that feels impossible, almost absurd. How do you weigh something you're standing on? You can't just pop the Earth on a scale. You can't compare it to anything. The whole task sounds more like a riddle from mythology than a problem for science. And yet, in the late 18th century, Henry Cavendish solved it. His bizarre and brilliant experiment, carried out with a fanatical obsession for precision, was about to pull back the curtain on one of nature's biggest secrets. The impossible problem. To really get the sheer audacity of what Cavendish was trying to do, we need to jump back another century, to the titan of science himself, Isaac Newton. Newton gave us the law of universal gravitation, a beautifully elegant equation that described the dance of the cosmos. He figured out that every object in the universe attracts every other object. The force of this attraction, he said, depends on two things: how massive the objects are and how far apart they are. The more massive, the stronger the pull. The farther apart, the weaker it gets. It's all described by his famous equation: F equals g times the product of the two masses, divided by the square of the distance between them. This single line of math could explain why an apple falls from a tree and why the moon orbits the earth. It was a revolution. But there was a ghost in the machine, a piece of the puzzle that was completely missing. It was that letter, G. G stands for the gravitational constant. Think of it as the universe's master volume knob for gravity. It's the number that sets the strength of this force everywhere, for all time. Without knowing the value of G, Newton's grand equation was powerful but also frustratingly incomplete. You could use it to understand the asterisk relationship between planets. For instance, you could figure out that the Sun was about 330,000 times more massive than the Earth without knowing the actual mass of either. But you couldn't figure out the absolute mass of a single one of them. It was like having a perfect recipe that called for some flour, but didn't tell you if you needed a cup or a kilogram. Scientists knew the Earth's radius, and they could measure how fast things accelerate towards the ground, that familiar 9.8 meters per second squared. They had all these pieces, but they couldn't find the planet's total mass. The problem was the sheer, unbelievable weakness of gravity. Gravity is, by a ridiculously huge margin, the weakest of the four fundamental forces of nature. The electromagnetic force holding atoms together, for example, is about 1,000 trillion times stronger. You prove this every time you pick something up. The tiny electrical bonds in your arm muscles are effortlessly overpowering the gravitational pull of an asterisk entire planet. This incredible weakness meant that trying to measure the gravitational pull between two objects you could actually hold in a lab was thought to be impossible. The force would be so tiny, so infinitesimal, that it would be completely drowned out by the slightest vibration, the tiniest gust of air, or even the body heat from a person standing nearby. So, the challenge was twofold. First, you had to build something sensitive enough to even detect a force that was practically non-existent. And second, you had to isolate it so perfectly from the outside world that you could be sure you were measuring gravity, and not just a draft. For nearly 100 years after Newton, G remained a mystery, and the mass of the Earth was just an educated guess. Weighing the world seemed less like a scientific challenge and more like a fool's errand. The eccentric genius. To take on a problem this absurdly difficult, you needed a very particular kind of person. And Henry Cavendish was nothing if not particular. Born in 1731 into one of Britain's wealthiest aristocratic families, he was, as one biographer put it, the richest of all the savants and the most knowledgeable of the rich. Yet this immense wealth seemed to have almost no effect on his life. He lived like a hermit, driven by an insatiable scientific curiosity and a pathological shyness. Cavendish was a creature of unshakable habit. He wore the same old-fashioned, drab suit for his entire adult life. He ate the same meal, a leg of mutton, for dinner every single day. On one rare occasion when he was expecting 4 scientific colleagues, his flustered housekeeper asked what to prepare. "Get a leg of mutton," Cavendish replied. When she pointed out this wouldn't be enough, he thought for a moment and said, "Then get 2 legs." His aversion to social interaction was legendary, and he was especially terrified of women. He communicated with his female servants only through written notes left on a table. If he happened to meet a maid on the stairs, he was known to freeze in agitation. This led him to have a second, private staircase built in his grand mansion for the sole purpose of avoiding his housekeeper. His house was less a home and more a giant laboratory. The grand drawing room was a workshop, and his library was so huge he bought a separate house just to hold it, which he then rarely visited to avoid the other scholars who used it. His only real social outlet was the weekly dinner at the Royal Society Club, a gathering of the country's top scientists. Even there, he was a strange, silent figure. Members learned you weren't supposed to address him directly. Instead, you should wander near him, look off into the distance, and speak as if into vacancy. If your comment was scientifically interesting, you might get a mumbled, high-pitched reply. But more often than not, he'd just stand there, overwhelmed, before nervously scuttling away. This bizarre, reclusive behavior has led many modern historians and neurologists, like Oliver Sacks, to suggest that Cavendish may have been on the autism spectrum. His life was marked by extreme social difficulty, a preference for solitude and routine, and an intense, narrow focus on his interests. But that focus was his superpower. When he aimed his powerful intellect at a problem, his capacity for precision and concentration was unmatched. Before he ever tried to weigh the world, Cavendish had already made huge discoveries. He was the first person to isolate hydrogen gas, which he called inflammable air, and to show that this gas burned to produce water, revealing its composition for the first time. He did incredibly accurate experiments on the composition of the atmosphere, but noticed a tiny, stubborn bubble of leftover gas, about 1/120th of the total, that he couldn't identify. He just noted it down and moved on. A full century later, scientists discovered the inert gas argon, realizing Cavendish had detected its presence 100 years before anyone else. This was the man. A walking paradox. An aristocrat who lived like a monk. A brilliant mind trapped in a cage of social anxiety. He made world-changing discoveries and then often didn't bother to tell anyone. He wasn't driven by fame or fortune. He already had more than he could ever want. He was driven purely by the joy of knowing. And in 1797, this strange and brilliant man turned his obsessive attention to the biggest measurement of them all. The ghost of an idea. The story of the experiment to weigh the world doesn't actually begin with Henry Cavendish, but with another brilliant, and sadly overlooked, English scientist, John Michell. Michell was a geologist, an astronomer, and a true visionary. Years before anyone else, he was the first person to propose the existence of what we now call black holes. He was also the first to suggest that earthquakes travel in waves. Sometime before 1783, Michell came up with an ingenious way to measure the force of gravity in a laboratory. He designed and built a strange and wonderful new instrument to do it, the torsion balance. The idea was beautifully simple in theory, but fiendishly difficult in practice. Imagine a 6-foot wooden rod hanging horizontally from a very thin, delicate wire. At each end of the rod, there's a small lead ball. Now, if you bring two much larger, more massive lead balls close to the small ones, the faint gravitational attraction should, in theory, pull the small balls toward the big ones. This would cause the rod to rotate, twisting the wire it's hanging from. Of course, the wire resists being twisted. This is called torsion. The more you twist it, the more it wants to twist back. Eventually, the system will settle down, with the incredibly weak force of gravity pulling the balls together being perfectly balanced by the twisting force of the wire pulling them back. If you could measure that tiny angle of rotation, and if you knew exactly how much force it took to twist that specific wire by a certain amount, you could calculate the gravitational force between the lead balls. It was a stroke of genius, a way to take the weakest force in the universe and make it visible. Michell built the apparatus, but for reasons lost to history, maybe because of his failing health, he never finished the experiment. When John Michell died in 1793, his revolutionary device passed to a friend, who in turn gave it to the one man in England everyone knew had the skill, patience, and obsessive precision to make it work: Henry Cavendish. Cavendish got Michel's apparatus and, true to his nature, rebuilt it almost completely, making it even more accurate. He knew from the start that the biggest challenge wasn't the physics, it was the noise. The gravitational force he was trying to measure was, as he calculated, only about 1/50th, 0.00000th of the weight of the small balls of force, so small it's almost impossible to imagine. The slightest disturbance would ruin everything. So, Cavendish took extreme precautions. He put the entire torsion balance inside a sealed wooden box to protect it from air currents. But that wasn't enough. He knew his own presence in the room, his body heat would create tiny temperature changes and air movements that could mess up the delicate measurement. So, he took the extraordinary step of isolating himself from his own experiment. He put the whole apparatus in a separate, closed shed on his property. He then drilled 2 small holes in the wall of the shed. Through one hole, he used a telescope to watch the tiny movement of the balance arm. Through the other, he used a system of rods and pulleys to move the large lead weights into position from the outside, without ever entering the room. He had created a sealed world, a tiny universe containing just his instrument, which he could only peer into from afar. For nearly a year, from 1797 to 1798, Cavendish lived by the rhythm of his experiment. He would move the weights, and then wait. The balance would slowly begin to swing back and forth. Through his telescope, he would meticulously track the end of the rod, using a tiny ivory scale called a vernier to measure the movement to an accuracy of less than 1/100th of an inch. He wasn't just conducting an experiment. He was performing an act of pure, unadulterated scientific devotion. The way in. So, let's walk through what Cavendish was actually seeing through his telescope. The process was painstaking. First, with the 2 massive 350-pound lead spheres positioned away from the balance, the delicate arm with the small 1.6-pound spheres would hang still. That was his 0 point. Then, using his remote pulleys, Cavendish would swing the large masses into place. And then, the magic, or rather, the physics would happen. The invisible, infinitesimal force of gravity would begin its work. The large lead ball on one side would pull its smaller neighbor toward it. The same thing happened on the other side. The cumulative effect was a tiny, almost imperceptible twist on the wooden arm. The arm would start to rotate, twisting the thin fiber it was suspended from. As it twisted, the fiber fought back. The arm would swing past its new balance point, then swing back, oscillating in a slow, gentle dance. Cavendish couldn't just wait for it to stop moving. It would take forever. Instead, he meticulously recorded the extreme points of each oscillation. By averaging these readings, he could mathematically figure out the final resting point, the exact angle where gravity was perfectly balanced by the twisting of the wire. The total deflection he measured was minuscule, only about 0.16 inches at the end of the 6-foot rod. But how did he know the twisting force of the wire? This was the other half of his genius. He figured this out by timing the balance's natural oscillation period. Just like a pendulum's swing time depends on its length, the oscillation period of his torsion balance depended on the stiffness of the wire. By timing this slow dance, he could calculate exactly how much force it took to twist the wire by a given amount. Now he had everything. He had directly measured the gravitational force between objects whose masses he knew. He knew the distance between them. The only unknown left in Newton's grand equation was g. But here we come to a fascinating and often misunderstood point. Henry Cavendish did not set out to find g. In fact, the gravitational constant, g, as we know it, wouldn't even be defined or widely used by physicists for decades. Cavendish's paper was titled, "Experiments to Determine the Density of the Earth." His logic was brilliant. He had created a miniature solar system in his shed. He could measure the force between his small lead planet and his large lead Sun. He then compared this force to the force of gravity between that same small lead ball and the entire planet Earth, which was simply its weight. Since he knew the Earth's radius, the ratio of these two forces let him calculate the ratio of the Earth's density to the density of lead. He was, in his own words, weighing the world. After months of painstaking measurements, he arrived at his final result. He concluded that the average density of the Earth was 5.48 times the density of water. Let's pause to appreciate this. Today, with satellites and lasers, the accepted value is about 515 times the density of water. Working in a shed, using an instrument he built himself, Henry Cavendish had determined the density of the entire planet with an error of less than 1%. His accuracy would not be significantly improved upon for almost 100 years. It remains one of the most astonishing feats in the history of experimental physics. The key to the cosmos. With the Earth's density in hand, calculating its total mass was simple. Knowing the Earth's radius, you could calculate its volume. Multiply that by the density Cavendish found, and you get the final number. About 6 trillion kilograms. That's a 6 followed by 24 zeros, an almost incomprehensibly vast number, all derived from one of the smallest forces ever measured. But the true legacy of the Cavendish experiment goes far beyond just getting a number for our planet. Even though Cavendish himself didn't frame it this way, his experiment was the first ever measurement of the gravitational constant, g. Later physicists would take his data and use it to calculate g's value, finding it to be remarkably close to the modern value of 674 times 10. Finding g was like finding the Rosetta Stone for the cosmos. For the first time, Newton's law of universal gravitation was no longer just about proportions. It was a quantitative, predictive tool. With the value of g finally known, the dominoes started to fall. Scientists could now weigh the sun. By knowing the radius of Earth's orbit and the length of a year, they could use Newton's law, now complete with g, to calculate the sun's mass. Then they could weigh the other planets. By observing Jupiter's moons, for instance, astronomers could apply the same law to find the mass of Jupiter. Suddenly, the entire solar system could be placed on a cosmic scale. Cavendish's quiet, patient work in a secluded shed had provided the key to unlock the mass of the universe. His experiment also did something just as profound. It confirmed that Newton's law was truly universal. It showed that the very same force that gently tugged a tiny lead ball in a London laboratory was the same force that held the planets in their orbits around the sun. The laws of physics were the same for the heavens and the earth. It was a pivotal moment, transforming gravity from an abstract concept into a tangible, measurable part of reality. And it all came back to Henry Cavendish, the man who cared for none of the acclaim. He published his paper, a model of scientific clarity, and then just moved on to the next problem that caught his interest, in this case, his pioneering work in electricity. He never spoke of his achievement in grand terms. For him, the beauty was in the measurement itself. He had set out to find a number, and he had found it with near-perfect precision. What others did with that number was their business. The story of Henry Cavendish is a powerful reminder that sometimes the greatest revolutions in science don't come from the loudest voices, but from the quietest and most persistent minds. These are the kinds of hidden histories and surprising breakthroughs we love to share. If you find this kind of deep dive into science as fascinating as we do, consider subscribing and joining our community of curious minds. There are always more secrets to uncover. When Henry Cavendish died in 1810, he was one of the wealthiest men in Britain, having left his massive fortune largely untouched. He remained a recluse to the very end. His life was a study in contrasts. A man of immense privilege who lived with austere simplicity, a social outcast who was profoundly respected by his peers, and a prolific genius whose greatest discoveries were often confined to his private notebooks. For decades after his death, his scientific legacy was thought to be based on a handful of brilliant published papers. But then, in the 1870s, the physicist James Clerk Maxwell took on the huge task of editing Cavendish's unpublished manuscripts. What he found was shocking. Hidden in those pages was a scientific revolution in secret. Cavendish had anticipated the work of some of the 19th century's most famous scientists, often by decades. He had developed a comprehensive theory of electricity that included concepts like voltage and a version of Ohm's law, long before the men who would eventually get credit for them. He had done the experiments, worked out the theories, and then, in his typical fashion, simply filed the notes away. He had discovered it all for himself, and for him, that was enough. The Cavendish experiment stands as his most famous public achievement, a perfect fusion of his character and his intellect. It required a mind that could pose the grand cosmic question, how much does the world weigh? And combine it with an obsessive, almost fanatical attention to the tiniest details. He was a man who built a special staircase to avoid his housekeeper, and it was precisely that kind of mind, one that sought to control every variable and eliminate every possible disturbance, that was needed to isolate the whisper of gravity from the noise of the world. So the next time you think about the force of gravity, don't just think of Newton's apple. Think of Henry Cavendish in his sealed shed, peering through a telescope. Think of those two lead balls, locked in their slow, silent dance, revealing a fundamental truth about our universe. His story isn't just about a clever measurement. It's a testament to the power of pure curiosity, a demonstration that even the biggest questions in the universe can sometimes be answered by the quietest and most patient observer, working alone with a simple piece of wire and an unshakable desire to know. The real reason Earth is secretly gaining weight right now, at this very second, our planet is being bombarded. Not by anything you can see or feel, but by a constant, invisible storm from deep space. You probably think of Earth as a closed system, a perfect marble sealed off from the cosmos. You learned its mass in school, a fixed number. But that's not the whole story. See, our planet has a diet. For billions of years, it's been secretly bulking up, and the evidence is buried in the most remote place on Earth and written in the fiery trails of shooting stars. This isn't science fiction. This is a cosmic weight gain, and the numbers behind it are staggering. We live our lives on a planet that feels solid and stable. Its sheer scale gives us a sense of permanence. The ground beneath our feet is, well, it's grounded. But this feeling of stability is a beautiful illusion. Our world isn't some static rock floating in a sterile void. It's a dynamic body, constantly interacting with its environment, locked in a cosmic dance of give and take. Every single day, Earth is showered with material from space. It's an almost imperceptible rain of alien dust, mixed with the occasional, catastrophically violent delivery of rock and ice. We see fleeting glimpses of this on clear nights, when a meteor streaks across the darkness that's a tiny grain of sand from a distant comet, burning up in a final, brilliant farewell. But for every one you see, countless others complete their journey in secret. So, the real question isn't if Earth is gaining weight. The question is, how much? What's the true scale of this planetary weight gain program? To find the answer, we have to journey from the quietest, coldest continent on Earth to the most violent events our solar system can throw at us. We'll investigate an invisible rain that adds a shocking amount of weight to our planet every day, and we'll confront the civilization-altering power of giant asteroids. The story of Earth's secret weight gain is the story of our planet's connection to the universe itself. It reveals we aren't just living on a planet. We're part of a constantly evolving cosmic ecosystem. And it all starts with something so small, you could hold 1,000,000 of them in the palm of your hand. Cosmic dust. The invisible rain, cosmic dust. When you think of things falling from space, your mind probably jumps to flaming meteors or city-sized asteroids. Drama. Destruction. But the overwhelming majority of Earth's weight gain, the real star of our story, is far more subtle. It's a relentless, gentle, and almost entirely invisible shower of microscopic particles known as cosmic dust or micrometeorites. Scientists have a wide range of estimates, but they believe up to 40,000 tons of this material fall on Earth every single year. To put that number in perspective, 40,000 tons is about 110 tons per day. That's like the mass of a blue whale or a large commercial jet being added to our planet every 24 hours. It doesn't arrive in one big clump, of course. It's a fine, steady drizzle spread across the entire 510 million square kilometer surface of our world. Year after year, century after century, it adds up. So, what is this stuff, and where does it all come from? Cosmic dust is essentially the leftover construction material of our solar system. These are the crumbs from the cosmic table, particles ranging from a few molecules to the size of a grain of sand. They mainly come from two places: comets and asteroids. Think of comets as dirty snowballs, ancient relics from the outer solar system made of ice, rock, and dust. As a comet gets closer to the sun, the solar radiation heats its surface. The ice turns directly into gas, blowing away tiny grains of dust that were trapped inside. This creates a vast, dusty halo and a beautiful tail that can stretch for millions of kilometers. As Earth orbits the Sun, it regularly passes through these ancient debris streams. When it does, we get a meteor shower. The Perseids in August, the Leonids in November. Each shooting star is a tiny piece of cometary dust, no bigger than a grain of sand, incinerating itself in our upper atmosphere. The other major source is the asteroid belt between Mars and Jupiter. It's a surprisingly dynamic place where asteroids are constantly, slowly, bumping and grinding into one another. These collisions create enormous clouds of finer dust. Over millions of years, the subtle pressure of sunlight and gravitational nudges from planets can cause this dust to spiral inwards, eventually crossing Earth's path. Based on chemical analysis, it's now believed that the vast majority of cosmic dust reaching Earth, roughly 80%, originates from comets. Now, you might be asking a logical question. If a grain of sand burning up creates a brilliant shooting star, how does any of this dust actually reach the ground? It all comes down to physics, specifically, the ratio of surface area to mass. When a large meteoroid hits the atmosphere, it compresses the air in front of it, generating immense heat. It glows, ablates, meaning its surface layers are stripped away and most of it vaporizes. But a micrometeorite is different. Because it's so tiny, it has a huge surface area compared to its minuscule mass. This allows it to radiate heat away extremely efficiently. Instead of vaporizing, it's more like it hits a wall of molasses. It slows down rapidly without catastrophic heating, and then, its journey changes. It no longer plummets, it drifts. For weeks, these tiny particles of alien dust can float gently down through the atmosphere, eventually settling unnoticed on every surface of the planet. But how can scientists be sure? How do they separate this extraterrestrial dust from all the regular dust on Earth? For that, they had to go to the cleanest, most isolated place on the planet: Antarctica. For over 2 decades, international teams of scientists have made grueling expeditions to a place called Dome Sea, a high plateau deep in the Antarctic interior. It's over 1,000 kilometers from the coast, with average summer temperatures around -35 degrees Celsius. There's almost no terrestrial dust here. Just snow, which falls year after year, burying everything in distinct, clean layers. It's the perfect trap for cosmic dust. The process is painstaking. Researchers dig deep trenches to access snow layers that fell decades ago. They carefully melt enormous volumes of this ultra-clean snow and filter the water. What's left behind is a collection of tiny, dark particles. Under an electron microscope, their identity is clear. They have unique chemistries and structures that scream, "Not from this Earth." By analyzing the number of particles in a given volume of snow, the scientists could calculate a precise flux, the amount of dust falling over a certain area each year. After 20 years of work, they arrived at a figure. When extrapolated to the entire globe, the data from Dome C shows that at least 200 tons of this micrometeorite dust, specifically in the 30 to 200 micrometer size range, lands on Earth every year. This is considered a highly conservative, directly measured baseline, the proven, ground truth minimum. And it powerfully confirms our planet is continuously sweeping up the dust of the cosmos. The heavy hitters. Meteors and asteroids. That gentle, continuous rain of cosmic dust accounts for the vast majority of Earth's annual weight gain, but it's not the whole story. Sometimes, the universe doesn't send a drizzle, it throws a rock. This is where things get dramatic. First, let's get the terms straight. A meteoroid is a rock in space. When it enters our atmosphere and burns up, the streak of light we see is a meteor or shooting star. If any part of it survives and hits the ground, it's a meteorite. And this happens way more often than you'd think. While most incoming objects burn up, it's estimated that thousands of meteorites strike Earth each year. Most are small, pebble to fist-sized objects, and since 70% of our planet is water, most land completely unseen. But every now and then, one makes its presence known. The real drama, however, comes from the much rarer, much larger objects. An object the size of a car enters the atmosphere about once a year, usually exploding high above the ground. A rock the size of a football field might hit us every couple of thousand years, capable of causing regional devastation. And then there are the true monsters. For a modern-day example, we only need to look back to the morning of February 15, 2013. Residents of Chelyabinsk, Russia, were startled by a light in the sky that momentarily shone brighter than the sun. Minutes later, a deafening sonic boom shattered thousands of windows, injuring around 500 people, mostly from flying glass. The culprit? A near-Earth asteroid, about 20 meters, or 66 feet, across, with a mass of around 10,000 to 14,000 tons. It slammed into the atmosphere at over 60,000 kilometers per hour and exploded in an airburst. The energy released was estimated to be around 500 kilotons, about 30 times more powerful than the atomic bomb detonated at Hiroshima. In that single, violent moment, an object weighing thousands of tons was delivered to our planet. Much of its mass vaporized, but not all. Scientists descended on the region, and months later, a huge chunk weighing over 650 kilograms was pulled from the bottom of a frozen lake. The Chelyabinsk event was a stark reminder that Earth's weight gain isn't always gentle. But even Chelyabinsk was just a firecracker. To see what a truly heavy hitter can do, we have to go back 66 million years. At the end of the Cretaceous period, an object of almost unimaginable size, estimated to be between 10 and 15 kilometers in diameter, was on a collision course with Earth. Its mass would have been in the trillions of tons. It struck what is now the Yucatan Peninsula in Mexico, carving out a crater over 180 kilometers wide. The energy released was billions of times more powerful than an atomic bomb. It triggered a mega tsunami and blasted trillions of tons of vaporized rock and dust into the atmosphere, shrouding the planet in darkness. The resulting climate collapse led to a mass extinction that wiped out 75% of all species, including the non-avian dinosaurs. When we talk about Earth gaining weight, the Chicxulub impactor represents the ultimate delivery. In a single day, it added a staggering amount of extraterrestrial mass. Of course, the impact also blasted a huge amount of Earth's own crust into space. But the net addition of the impactor's material left an undeniable chemical signature in rock layers around the world, providing proof of this colossal weight gain event. The Cosmic Balancing Act. The plot twist. So, we have a planet that's been relentlessly pelted with cosmic material for billions of years. It's showered with dust and occasionally smashed by asteroids. The logical conclusion seems simple. Earth must be getting heavier. But here's where the story takes a sharp turn. Because at the very same time Earth is feasting on cosmic dust, it's also, paradoxically, on a diet. Our planet is constantly losing mass, leaking it away into the void. To understand this, we have to look at our atmosphere. It isn't a sealed lid. It's a vast ocean of gas held down by gravity, and its outer edges are exposed to space. The main culprits in this story of mass loss are the two lightest elements: hydrogen and helium. High up in the exosphere, the outermost layer of our atmosphere, these lightweight atoms are zapped with energy from the sun. If an atom gets moving fast enough, faster than Earth's escape velocity of about 11.2 kilometers per second, gravity simply can't hold on. The atom zips away, lost from Earth forever. This process is called atmospheric escape, and it's happening right now. It's a slow, steady bleed of our atmosphere's lightest components. Think of it like steam rising from a pot of water. Most of our atmosphere heavy molecules like nitrogen and oxygen is held firmly by gravity. But hydrogen and helium are the escape artists. So, how much are we losing? Scientists have done the math. Every year, Earth loses approximately 95,000 tons of hydrogen and about 1,600 tons of helium to space. Add those up, and you get a total atmospheric loss of roughly 100,000 tons per year. Now, let's do the cosmic math. On one side of the scale, we have the incoming material. Let's use the high-end estimate of about 40,000 tons per year from dust and meteorites. On the other side, we have the outgoing material, about 100,000 tons per year of lost gas. When you balance the scales, the result is undeniable. The loss is greater than the gain. The net result is that Earth is actually losing mass, shedding roughly 50,000 to 60,000 tons every single year. The real reason Earth is gaining weight is this complex balancing act. It gains weight from space, but it loses even more from its own atmosphere. Now, before you worry that our planet is wasting away, let's put this in perspective. A loss of 50,000 tons a year sounds like a lot. But Earth's total mass is about 6 sextillion kilograms. That's a 6 followed by 24 zeros. Losing 50,000 tons per year is like an 80-kilogram person losing the mass of a single eyelash. It would take trillions of years for this to have any noticeable effect on Earth's gravity or orbit. Long before our atmosphere could ever bleed away, our sun will have become a red giant, making the whole question irrelevant. But the fact that this exchange is happening at all is profound. It shatters the image of Earth as an isolated island. Instead, it paints a picture of a planet that is breathing. It inhales dust from the cosmos and exhales its lightest gases back into the void. It's this kind of cosmic perspective that we love to explore. This constant exchange between our planet and space has shaped our world and reminds us how interconnected everything truly is. If you enjoy having your mind expanded by the incredible, hidden workings of the universe, make sure you're subscribed and have clicked that notification bell, because you won't want to miss where we're going next. Why it matters. So, we've established this incredible cosmic balancing act, with the net result being a tiny, insignificant annual weight loss. It's a fascinating piece of trivia, but does it actually matter? The answer is a resounding yes. First, that incoming material is a scientific treasure trove. Those tiny particles of cosmic dust are direct samples of asteroids and comets. Instead of launching a multi-billion-dollar spacecraft, we have a constant delivery service. By collecting this dust in places like Antarctica, we can learn about the raw ingredients that built the planets 4-5 billion years ago. What's more, these micrometeorites might have played a key role in the origin of life. We know cosmic dust contains not just rock and metal, but also water and complex organic compounds like amino acids, the building blocks of proteins. In the early days of the solar system, this constant delivery could have seeded the young Earth with the ingredients necessary for life to emerge. Now, what about the heavy hitters? Understanding the flow of asteroids isn't just about curiosity, it's about survival. The Chelyabinsk event in 2013 was a global wake-up call. An object just 20 meters across, completely undetected, caused significant damage and injuries. Studying the rate at which these objects hit Earth allows us to build statistical models of risk and informs the entire field of planetary defense. Projects like NASA's DART mission, which successfully altered an asteroid's orbit, are a direct result of this understanding. We're taking the first steps to protect ourselves from the same fate that befell the dinosaurs. Finally, on a more philosophical level, this whole process fosters a sense of profound connection. The iron in your blood was forged in the heart of a long-dead star. How did it get here? It may well have been delivered to Earth inside an asteroid or a grain of cosmic dust billions of years ago. The ground beneath your feet isn't just rock, it's a graveyard of comets and a museum of shattered asteroids. Realizing that our planet is breathing, inhaling the dust of the solar system and exhaling its lightest elements reframes our place in the universe. We aren't on a self-contained spaceship. We are part of a vast, interconnected, and dynamic environment. The picture of Earth as a static, isolated sphere is, in the end, a convenient fiction. The reality is infinitely more poetic. Our planet is alive, engaged in a subtle, billion-year-long dance with the cosmos. Every day, it sweeps up thousands of tons of ancient history in the form of cosmic dust, the remnants of creation itself. And every day, it gently releases its most ethereal elements back into the void. This isn't just a story of mass gained or lost. It's a story of connection. A reminder that the boundary between Earth and space is not a wall, but a permeable membrane. The universe isn't just out there, it's constantly arriving here, becoming part of our world, part of our soil, and perhaps, even part of us. So the next time you're outside on a clear, dark night and see a shooting star flare for a brilliant instant, take a moment. Don't just see a flash of light. Recognize it for what it is. A tangible piece of the solar system completing its long journey. It's a microscopic messenger, carrying secrets from the birth of the planets and delivering itself to our world. It's the real and beautiful reason our planet is in a constant state of becoming, forever tied to the grand, cosmic ocean in which it drifts. Earth's invisible shield is vaporizing invaders from space. Every single day, our planet is under attack. Thousands of tons of rock and dust, leftovers from the birth of our solar system, are plummeting towards us at unimaginable speeds. But we don't live on a crater-pocked world like the moon. Why not? Because Earth has an invisible shield. And that shield is waging a fiery, silent war on these invaders. But here's something you might not know. The way these space rocks are obliterated has almost nothing to do with friction. The real reason is far more violent. And what about the few that actually survive? Do they make our planet heavier? We've run the numbers, and the answer is not what you'd expect. The Cosmic Shooting Gallery. To understand the war in our skies, you first have to know what we're up against. The space between planets isn't empty. It's a cosmic shooting gallery, filled with debris from 4-6 billion years of solar system history. We're flying right through a constant, unrelenting hailstorm of cosmic particles. NASA estimates that every day, about 48 5 tons of this stuff is aimed right at our planet. That's almost 18,000 tons a year, a stream of cosmic dust and rock that never, ever stops. Out in the void of space, these objects are just drifting. They're no threat at all. But when their orbit crosses ours, they transform from quiet wanderers into blazing projectiles. Now, to really get what's happening, it helps to know the lingo, because a single word can mean the difference between a harmless light show and a catastrophe. The terms meteoroid, meteor, and meteorite get thrown around a lot, but they describe 3 very different stages of a cosmic journey. Let's start at the source. The asterisk meteoroid. This is the object while it's still in space. Think of it as a cosmic vagabond. Meteoroids can be tiny, like a grain of sand, or they can be massive, boulder-sized chunks of rock and metal. Most are orphans of the solar system, fragments chipped off asteroids during violent smash-ups in the asteroid belt, or dusty trails left behind by comets. Some are even pieces of other worlds. Ancient impacts on Mars or our moon have been so powerful they've launched planetary crust into space, sending it on a journey that can last for millions of years. So, a meteoroid isn't just a rock. It's a time capsule from another part of our solar system. Every day, thousands of these meteoroids end their journey at Earth. The moment one crosses the threshold of our atmosphere, usually about 100 kilometers, or 62 miles up, it changes. It stops being a meteoroid and becomes a asterisk meteor. This is the event, the brilliant streak of light we call a shooting star. This is where our invisible shield kicks into high gear. The meteoroid hits our atmosphere at blistering speeds, anywhere from 25,000 to 160,000 miles per hour. The air in front of it simply can't get out of the way fast enough. The result is intense compression and heating that creates a spectacular, and usually final, flash of light. Most meteoroids are completely vaporized during this phase, turned into a fine dust that slowly, harmlessly settles to the ground. The vast majority of shooting stars you see are caused by particles no bigger than a pebble, burning up in a split second of glory. But what if the meteoroid is made of tougher stuff? What if it's big enough or dense enough to survive that hellish descent? If any piece of the original rock makes it all the way to the ground, it gets a new name. A asterisk meteorite. This is the survivor. The veteran of the atmospheric war. Meteorites are our only tangible connection to the cosmos, actual samples from other worlds that we can hold in our hands. They often show the scars of their journey, like a dark, glassy outer layer called a fusion crust, which is the rock that melted and then re-solidified as it tore through the air. So, you have the asterisk meteoroid asterisk in space, the asterisk meteor asterisk in the sky, and the asterisk meteorite asterisk on the ground. Understanding that journey is key, because it sets up the central drama. Countless meteoroids arrive, they create meteors, but only a tiny fraction ever become meteorites. So what is it about that fiery trip through the atmosphere that's so good at destroying them? It's not what you think. The shield. How the atmosphere fights back. For as long as we've watched shooting stars, the common explanation has been friction. The idea that a space rock rubs against air molecules and heats up until it burns makes sense, right? It's like rubbing your hands together to warm them up, just on a cosmic scale. And it's almost completely wrong. While friction plays a tiny role, the real killer is something far more powerful: adiabatic compression. Think about a simple bicycle pump. When you pump up a tire, the pump gets hot, especially near the nozzle. Is that from the plunger rubbing inside? Not really. The heat you feel is the result of you rapidly compressing air. You're forcing air molecules into a smaller space, and the work you're doing is converted directly into heat. Now, scale that up to cosmic speeds. A meteoroid isn't gently pushing air aside. It's slamming into our atmosphere dozens of times faster than a rifle bullet. The air molecules in its path don't have time to flow around it. Instead, they pile up in front, forming an incredibly dense, high-pressure shockwave. This wall of air is compressed so violently and so fast that its temperature skyrockets to several thousand degrees Celsius hotter than the surface of the sun. It's this pocket of superheated plasma that does the real damage. The meteoroid isn't burning up from rubbing against the air. It's being incinerated by the intensely hot plasma cushion it creates in front of itself. The rock is flying into its own personal blast furnace. This process, where the surface is vaporized layer by layer, is called asterisk ablation. The intense heat literally peels the rock away, atom by atom. The beautiful colors you see in meteor streaks? That's the ablation happening in real time. The colors are the spectral fingerprints of the elements being vaporized. A bright yellow or orange glow means sodium. Iron, a common ingredient, burns with a golden light. Magnesium creates a brilliant blue-green, while silicate rock can glow reddish. The sky itself even gets in on the act, as superheated nitrogen and oxygen in our own atmosphere light up. Watching a meteor is like witnessing a high-speed, cosmic chemistry experiment. This whole fiery ordeal happens in a sweet spot in our upper atmosphere called the asterisk mesosphere asterisk, between 50 and 85 kilometers up. Here, the air is just dense enough to create that crushing pressure and heat, but still thin enough for the rock to be moving at insane speeds. As it plows deeper, the pressure becomes unbearable. For many meteoroids, this is the final straw. The rock doesn't just burn. It catastrophically disintegrates in a violent asterisk airburst asterisk, a flash of light that marks its final moment. The shield's effectiveness really comes down to the meteoroid's size, speed, and what it's made of. The overwhelming majority of that 48.5 tons of daily material is just dust and sand. For these tiny invaders, the battle is over before it begins. Even pebble-sized objects, which can create spectacular fireballs, rarely survive. They just don't have enough mass to make it through. It's a breathtakingly effective defense. A silent, fiery war is being fought miles above our heads every second, and our atmosphere is winning. But as good as it is, the shield isn't perfect. And every so often, an invader comes along that's too big, too strong, or too fast to be stopped. When the shield fails, the ones that get through. So what happens when the shield isn't enough? What happens when a meteoroid is so large that ablation can't finish the job? This is where the story shifts from a light show to a lesson in pure kinetic energy. The destructive power of an impactor is less about its size and more about its speed. The formula for kinetic energy is K equals 1/2 mv squared. The most important part of that is the v squared. It means if you double an object's mass, you double its energy. But if you double its speed, you quadruple its energy. And space rocks are moving ridiculously fast. A meteoroid the size of a car hitting the atmosphere at 40,000 miles per hour doesn't just pack the energy of a car crash. It packs the punch of a small nuclear weapon. For most of these larger objects, the end comes not from burning up, but from tearing itself apart in a massive explosion called an asterisk airburst. We have a terrifyingly recent reminder of what that looks like: the Chelyabinsk event. On February 15, 2013, a 20-meter-wide meteoroid about the size of a 6-story building hit the atmosphere over Russia at over 40,000 miles per hour. It never hit the ground. Instead, about 18 miles up, it detonated. The explosion was 30 times more powerful than the atomic bomb dropped on Hiroshima. The flash temporarily outshone the sun and gave people on the ground instant sunburns. Minutes later, the shockwave arrived. It shattered windows in thousands of buildings across 6 cities and injured over 1,500 people, mostly from flying glass. And yet, it left no crater. All that devastation was caused by an object our atmosphere stopped from hitting the surface. Go back to 1908 and you get the Tunguska event in Siberia. An even larger object, maybe 100 meters across, detonated in another airburst. It flattened over 2,000 square kilometers of forest, an area the size of Tokyo. If it had happened over a major city, millions would have died. Again, no crater. Sometimes, fragments do survive. The 1969 Allende event in Mexico was different. A car-sized meteoroid broke apart and rained down over 2 tons of fragments. These Allende meteorites became a scientific treasure trove, containing minerals older than the Earth itself. And then there's the ultimate shield failure, the Chicxulub impactor. 66 million years ago, a rock between 6 and 9 miles wide slammed into the Yucatan Peninsula. It was too big for the atmosphere to have any effect. The impact released the energy of billions of atomic bombs, triggering a global firestorm and a cosmic winter that led to the extinction of 75% of all species, including the non-avian dinosaurs. Thankfully, events on that scale are incredibly rare. But the daily influx of dust and gravel is constant. NASA and other agencies are always tracking larger objects, and so far, there are no known city killers on a collision course. Our shield holds strong. But it raises a fascinating question. With all this material raining down, is our planet slowly gaining weight? We've seen the shield and the invaders that breach it. The sheer physics is mind-bending. If you're finding this cosmic battle as fascinating as we do, take a moment to hit that subscribe button. It helps us keep exploring these huge questions. Now, back to the biggest question of all. The planetary weigh-in. The big weigh-in. Does Earth gain weight? Okay, this is where the story takes a surprising turn. We know Earth is constantly being showered with about 40,000 tons of extraterrestrial material every year. 40,000 tons. That's like adding 4 Eiffel Towers to the planet's mass every single year. So, you'd think, with that constant influx, Earth must be getting heavier. And you'd be right. Every speck of cosmic dust that settles adds its mass to our planet. So, case closed? Earth is gaining weight. Not so fast. Because Earth isn't just gaining mass, it's also losing it. The process is called atmospheric escape. Our atmosphere is a sea of gas, held by gravity. But at the very top, in the exosphere, you find the lightest elements: hydrogen and helium. These atoms are constantly being energized by the sun. Every so often, an atom of hydrogen or helium gets zapped with enough energy that it hits escape velocity. It starts moving so fast that Earth's gravity can't hold on, and it zips off into space, lost forever. How much are we losing? Scientists have done the math. Every year, Earth loses about 95,000 tons of hydrogen and 1,600 tons of helium. That's a combined loss of over 96,000 tons of mass every single year. There are other tiny losses, too, like a bit of mass converted to energy by radioactive decay deep in the core, and the satellites we launch into deep space. So let's do the final tally. In the gone column, we have about 40,000 tons per year from cosmic dust and meteorites. In the loss column, we have over 96,000 tons from atmospheric escape, plus a few dozen other tons from miscellaneous sources. When you balance the books, Earth has a net loss of around 57,000 tons every year. Our planet isn't gaining weight, it's on a very, very slow diet. The invaders from space aren't enough to tip the scales. Now, before you panic about our planet wasting away, let's put that number in perspective. 57,000 tons sounds like a lot, but Earth's total mass is about 5,972 sextillion tons. That's a 6 with 21 zeros after it. Losing 57,000 tons a year is like an elephant losing a single eyelash. It's an infinitesimally small fraction that has absolutely no effect on our planet's gravity, orbit, or future. So while the invaders from space do technically add mass, their contribution is completely dwarfed by the quiet, steady leak of gas from the top of our atmosphere. When you pull back and look at the big picture, it's pretty incredible. Every day, our planet weathers a relentless bombardment from space. But we're protected by our atmosphere, which uses the wild physics of compressive heating to wage a silent, fiery war on these intruders, vaporizing almost all of them into beautiful, fleeting streaks of light. It's not friction, but a self-generated plasma furnace that does the destroying. We've seen the terrifying power of the few that get through, like the Chelyabinsk meteor. And in the end, we did the math, discovering that while thousands of tons of space stuff falls on us each year, even more of our own planet is slowly escaping into the void. The real story here isn't about gaining or losing a few tons. It's about the astonishing balance of forces that makes our world possible. Our atmosphere is more than a shield. It's a dynamic filter, a complex system that stands between us and the raw violence of the cosmos. It silently incinerates threats, gives us air to breathe, and all the while, it's slowly leaking its own atoms back into the void it protects us from. So the next time you're out on a clear night and you see a shooting star, don't just make a wish. Take a second to appreciate the extraordinary physics you just witnessed. Think about that invisible shield, holding strong 60 miles above your head. And it makes you wonder, what other invisible forces are shaping our world, right under our noses? Earth's bizarre diet: it eats dust but still loses weight. Every single day, our planet gets showered with stuff from space. A constant, glittering rain of dust falls on us from the void, adding to our world's mass, hour by hour. By all accounts, Earth should be getting heavier. It's on a perpetual feast of cosmic debris. And yet, it's losing weight. Like a cosmic heavyweight who eats non-stop but somehow sheds pounds, our planet has a bizarre paradox on its hands. It's constantly gobbling up tons of space dust, but the scales are slowly, imperceptibly, tipping the other way. Earth is getting lighter. So, what's going on? How can our world be on a constant, planet-sized binge and still be slimming down? This is the story of that strange contradiction, a cosmic tug-of-war between gaining and losing. To figure it out, we need to look in two directions. Up, at the endless rain of material falling from space, and back down, at the very air we breathe, which is quietly slipping away. The feast. Earth's cosmic appetite. Let's start with the easy part of the equation. Earth's constant meal. Every day, our planet plows through a vast, invisible cloud of particles on its trip around the sun. The space we're moving through isn't a pristine vacuum, it's more like a dusty old attic. And all that dust has to go somewhere. That somewhere is here. So what is this cosmic dust? It's not the city-destroying asteroids you see in movies. Think smaller. Much, much smaller. We're talking about micrometeorites, tiny grains, often no bigger than a speck of sand. These are the leftovers from our solar system's construction project that wrapped up about 4.5 billion years ago. Their origins are ancient and varied. Many are the pulverized remains of asteroids that have been smashing into each other for eons out in the asteroid belt. Like a cosmic fender bender, these collisions create clouds of debris, and some of it gets knocked into an orbit that crosses paths with ours. Another major source is comets. As these icy wanderers swing toward the sun, they heat up. The ice turns to gas, spewing out a trail of dust and rock. This creates a spectacular tail, a river of debris that keeps orbiting the sun. When Earth passes through one of these old dust trails, we get a meteor shower, like the Perseids in August. While we see the bigger pieces burn up as shooting stars, we're also getting pelted by countless microscopic particles, too small to make a visible streak. Now for the big question. How much of this stuff is Earth actually collecting? Scientists have gone to incredible lengths to figure this out. They've used radar to track incoming meteors, flown special planes to catch the dust as it falls, and, most effectively, they've gone to the cleanest place on Earth to find it: Antarctica. For over 2 decades, researchers have traveled to a remote spot called Dome C. It's a perfect laboratory buried under miles of ice with an incredibly low amount of local, terrestrial dust. By carefully digging up pristine layers of snow, melting it, and isolating the extraterrestrial particles, they can calculate a global average. The number they've landed on is pretty staggering. Every year, our planet gains somewhere between 40,000 and 50,000 metric tons of mass from this cosmic dust. Let's put that number in perspective. 40,000 tons is about 110 tons per day. It's like the weight of an adult blue whale raining down on Earth every day and a half. Imagine 10 large dump trucks, full of fine, dark dust, backing up to our planet and dumping their payload every single day. Most of these particles, even the tiny ones, arrive at blistering speeds tens of thousands of miles per hour. As they hit the upper atmosphere, friction vaporizes most of them into a puff of meteoric smoke. These are the shooting stars we wish upon. But a surprising amount survives. The smallest particles, the micrometeorites, are slowed down gently by the atmosphere, which acts like a brake. They drift down for weeks or even years, eventually settling on every square meter of our planet. They land in oceans, on mountains, and yes, on your roof. Right now, there are almost certainly microscopic bits of asteroids and comets in the dust around you. They're a silent, invisible reminder that we're part of a much larger, messier cosmic neighborhood. So, the case seems clear. Earth is under a constant barrage of space stuff, sweeping up tens of thousands of tons of debris year after year. It's simple addition, right? Well, this is only half the story. Because at the exact same moment our planet is feasting, it's also shedding an even greater amount of weight in a completely different, and far less obvious, way. The Great Escape. Earth's leaky atmosphere. If you thought 40,000 tons of incoming dust was a lot, get ready for a surprise. It turns out that while Earth is gaining all that mass, it's losing even more. The culprit isn't rock or dust. It's our own atmosphere. Our planet has a leak. This isn't a dramatic pop, but a slow, silent, and relentless process called atmospheric escape. Every second, a tiny fraction of our atmosphere gets going so fast that it overcomes Earth's gravity and drifts off into space, never to return. Now, not all of our atmosphere is in danger. The air you're breathing, mostly nitrogen and oxygen, is way too heavy and held too tightly by gravity to just float away. The real escape artists are the lightweights: hydrogen and helium. Think of a helium balloon you let go. It rises simply because it's lighter than the air around it. On a planetary scale, hydrogen and helium atoms do the same thing. When they're in the upper reaches of the atmosphere, they float to the very top. Let's look at these two individually. First, hydrogen. We lose an astonishing 95,000 metric tons of hydrogen to space every year. That's about 3 kilograms every single second. The main source is water. High up in the atmosphere, intense ultraviolet sunlight zaps water molecules, hydrogen oxide, splitting them apart in a process called photodissociation. It's like a microscopic karate chop. The heavier oxygen atom sticks around, but the now free hydrogen atoms are incredibly light and start drifting up towards space. Then there's helium. We lose about 1/600 tons of it annually. The helium in our air has a much more exotic origin. It's born from the Earth itself. Deep in the crust, radioactive elements like uranium and thorium slowly decay, releasing what are called alpha particles, which are just helium nuclei. This helium gets trapped for eons before seeping up to the surface and into the air. Just like hydrogen, its extreme lightness sends it on a one-way trip to the top. So we have this constant supply of light gases rising to the very edge of our atmosphere, a region called the exosphere. It begins about 600 kilometers up, and it's a bizarre place. The atmosphere there is so thin that atoms can travel for miles without bumping into each other. They behave less like a gas and more like a collection of individual ballistic particles. And this is where the escape happens. The main escape mechanism is a process called *Jeans escape. To break free from Earth's gravity, a rocket or an atom needs to be traveling at about 11.2 kilometers per second over 25,000 miles per hour. Anything slower, and gravity eventually pulls it back. In the incredibly hot, sun-drenched exosphere, temperatures can soar over 1,000 degrees Celsius. While the average speed of a hydrogen or helium atom isn't quite fast enough to escape, some atoms, just by random chance, get an extra energetic kick. They get jostled until their speed surpasses that critical 11.2 kilometers per second. Imagine a pot of boiling water. The most energetic molecules leap off the surface as steam. Jeans escape is the planetary version of that. In the hot exosphere, the fastest hydrogen and helium atoms simply shoot off into space, gone forever. Heavier atoms like oxygen and nitrogen are like cannonballs compared to the feather-light hydrogen and helium. At the same temperature, they move much more slowly and never get close to escape velocity. They are bound to our world. So let's do a quick tally of the losses. We're leaking about 95,000 tons of hydrogen and another 1,600 tons of helium every year. That's a combined loss of roughly 97,000 tons of our planet's mass, vanishing into space annually. But this isn't the only force at play. There's another, more violent one, a relentless bully from our own star that's constantly trying to sandblast our atmosphere away. The solar bully. A relentless wind. The space around our planet isn't a peaceful void. It's a battlefield. And the main aggressor is our own sun. The sun doesn't just radiate light, it spews a constant stream of charged particles called the solar wind. This isn't a gentle breeze. It's a supersonic plasma, screaming outwards at over 1 million miles per hour. And it's aimed right at us. If Earth were unprotected, this solar wind would act like a cosmic sandblaster, eroding our atmosphere over geologic time. To see the devastating consequences, we just have to look at our neighbor, Mars. Today, Mars is a cold, desolate world with an atmosphere less than 1% as thick as Earth's. But billions of years ago, it likely had a thicker atmosphere, was warmer, and had liquid water. So what happened? Mars lost its global magnetic field. Without that shield, the solar wind had direct access to the Martian atmosphere. For billions of years, high-energy particles slammed into the air, knocking it out of orbit and flinging it into space. This process stripped Mars of its air and turned a potentially vibrant world into a frozen desert. So why hasn't that happened to us? Because Earth has a planetary force field. The magnetosphere. Deep in our world, the churning of a liquid iron outer core generates a powerful magnetic field that surrounds our planet, stretching thousands of miles into space. This is our magnetosphere, and it's the single most important reason life exists today. When the solar wind approaches Earth, it collides with our magnetic field, which deflects the vast majority of these charged particles, forcing them to flow around us like water around the bow of a ship. It creates a protected bubble, a safe harbor in the cosmic storm. But the shield isn't perfect. Its most dramatic weaknesses create the auroras, the northern and southern lights. The magnetic field lines funnel down at the poles, creating openings where some solar wind particles can get channeled into the upper atmosphere. When they slam into oxygen and nitrogen, they make them glow in brilliant curtains of light. The aurora is a beautiful reminder of the constant battle being waged just above our heads. These openings are also a route for atmospheric escape. It's not just solar wind coming in. Some of our own atmospheric particles get caught and sucked out along these open field lines. This polar wind escape acts like a small fountain, spraying our atmosphere into space. So our magnetic field is a double-edged sword. It deflects over 99% of the solar wind that would otherwise strip our atmosphere away, but it also creates vulnerabilities at the poles that allow a small, steady leak. The solar bully is always knocking, and sometimes it manages to steal a few things. The final tally, doing the cosmic math. We've now seen both sides of this cosmic paradox. On one hand, our planet is feasting. On the other, it's perpetually leaking. So, is Earth getting heavier or lighter? Let's step on the cosmic scale. First, the mass gain. Earth is constantly bombarded by interplanetary dust. Scientists estimate this adds up to between 40,000 and 50,000 metric tons of mass every single year. Let's use a solid average and call it 45,000 tons gained. Next, the mass loss. Our atmosphere is steadily leaking its lightest elements. The main escapee is hydrogen, at a rate of about 95,000 tons per year. Then there's helium, leaking at around 1,600 tons per year. Add those together, and you get a total atmospheric loss of about 96,600 tons per year. Are there any other factors? Sure, but they're tiny. Earth's core loses about 160 tons per year as it converts a tiny amount of mass into heat through radioactive decay. And when we launch spacecraft on escape trajectories, we lose about 65 tons per year. Both are rounding errors in the grand scheme of things. So, let's get back to the main numbers. Total gain. Approximately 45,000 tons per year. Total loss. Approximately 96,600 tons per year from atmospheric escape. The math is pretty straightforward. 96,600 tons lost. Minus 45,000 tons gained. The verdict is in. Earth has a asterisk net loss of roughly 51,600 metric tons every year. Let's round that to a simple 50,000 tons. Our planet is, without a doubt, getting lighter. The cosmic diet is real. Every year, Earth is about 50,000 tons lighter than it was the year before. That's like jettisoning the mass of a modern aircraft carrier into space every couple of years. The dust from space is a hefty meal, but the atmospheric leak is a much bigger deal. The tug of war is happening, and the forces of escape are winning. So, there's our answer. Earth is on a bizarre diet, gobbling up tens of thousands of tons of cosmic dust while losing an even greater amount of its own atmosphere. The net result is a loss of about 50,000 tons of mass every year. This brings up a pretty urgent question. Should we be worried? Is our planet going to waste away and end up like Mars? The answer is a resounding no. While 50,000 tons sounds like a huge number to us, on a planetary scale, it's almost nothing. The total mass of the Earth is about 5.97 billion trillion tons. Losing 50,000 tons a year is like an adult human losing a single eyelash. The percentage of mass lost is a decimal point followed by 15 zeros. It's an infinitesimal fraction. At this rate, it would take trillions of years for our atmosphere to significantly deplete. For context, our sun will run out of fuel and become a red giant in about 5 billion years, swallowing Earth in the process. So, long before our atmosphere has a chance to trickle away, our entire planet will be gone. The slow leak is a fascinating scientific curiosity, not an existential threat. This isn't a story of impending doom, it's a revelation. It shows that our planet isn't some static, isolated rock. It's a dynamic system, locked in a constant, invisible dance with the cosmos. It breathes, it interacts, it changes. The next time you're outside on a clear night and see a shooting star, remember what you're really seeing. You're watching a tiny piece of an asteroid, born millions of years ago, ending its journey by becoming part of our planet. You're seeing Earth eat. And at that same moment, high above you, at the absolute edge of space, a few trillion hydrogen atoms, energized by the sun, are taking their final leap, leaving their home world behind forever. You can't see it, but at that moment, Earth is also losing weight. You're bearing witness to both sides of a grand, cosmic paradox, a planetary tug-of-war that, for now, our planet is slowly, and gracefully, losing. If you found this cosmic paradox as fascinating as we do, you might be interested in our video exploring what would happen if Earth's magnetic field suddenly disappeared, which you can watch by clicking the link on your screen. And for more deep dives into the strange and wonderful workings of our universe, make sure to subscribe to our channel and hit that notification bell so you never miss a new exploration. The invisible wind bleeding our planet dry. Right now, at this very moment, our planet is leaking into space. It's not a violent explosion. It's silent, constant, invisible. A perpetual wind, not of air, but of individual atoms, is carrying our world away, molecule by molecule. Every single second, about 3 kilograms of our atmosphere are lost forever, cast out into the void. This isn't science fiction. It's a fundamental part of being a planet, an epic, unending tug-of-war between the immense gravity of our world and the relentless energy of our own sun. It's a battle every planet with an atmosphere has to fight. And the outcome of that battle is the single greatest factor in determining whether a world becomes a living biosphere or a dead, barren rock. So, the real question is, if our world is constantly leaking, why aren't we a frozen desert like Mars? What's protecting us in this silent, cosmic war? To find the answer, we have to journey to the very edge of space, where our world ends and the void begins. We need to understand this invisible wind. And in doing so, we'll understand just how fragile and how unbelievably resilient we really are. The arena. The edge of space. To get how a planet loses its atmosphere, you first need to see where it happens. Don't think of our atmosphere as one big thing, but as a series of layers, each with its own personality. We live down here in the troposphere, the dense, weather-filled basement. Above that, the stratosphere, mesosphere, and thermosphere get progressively thinner. The air gets colder, then weirdly hotter, as the pressure just plummets. Finally, hundreds of kilometers up, you reach the last frontier, the exosphere. The name comes from Greek for outer sphere. And up here, the air is so thin that the word air kind of stops making sense. Down on the ground, a molecule of air travels a few dozen nanometers before smashing into another one. But here in the exosphere, a particle can travel for kilometers without a single collision. This isn't a gas anymore. It's a collection of individual particles on ballistic trajectories, like countless tiny cannonballs launched from the world below. This is the arena, the launchpad for atmospheric escape. The starting line is a boundary at the bottom of this layer called the exobase, around 500 kilometers up. Below that line, a particle is still part of the team. It bumps into its neighbors, shares energy, and gets pulled back down. But once a particle crosses the exobase, it's on its own. If it's got enough speed, and it's pointed in the right direction, nothing can stop it. It will never hit another particle. It will never come back. It will be lost to space. So what gives it the right to break free? One number. Escape velocity. For any planet or star, there's a speed you have to hit to break its gravitational pull. For Earth, that speed is a staggering 11.2 kilometers per second. That's about 40,000 kilometers per hour. Throw a ball, and it falls back down. Launch a rocket at 8 kilometers per second, and it orbits the Earth, perpetually falling but always missing. But fire it at 11.2 kilometers per second, and it's gone for good. It'll coast away into the solar system, never to return. Every single particle in the exosphere plays by this rule. If it can hit that critical speed, it escapes. That's the game. And Earth is a tough opponent. Our planet's massive size gives it a deep, powerful gravity well. But it's not the only player here. The Sun is constantly pumping energy into the system, supercharging these tiny particles and giving them a shot at making that final leap. This is where the battle really begins. The slow, silent heist, thermal escape. The most common way our atmosphere escapes the one happening right now is a process called thermal escape. Its more formal name is Jeans escape, named after the British astronomer Sir James Jeans, who figured it out over a century ago. You can think of it as the slow, silent heist of our atmosphere, one atom at a time. To get it, you need to rethink what temperature really is. On a microscopic level, temperature is just motion. The hotter something is, the faster its atoms are jiggling around. But even in a gas at one temperature, not all particles move at the same speed. There's a whole distribution. Most particles cruise around an average speed, but you always have some slowpokes, and more importantly, you always have a few speed demons in what scientists call the energetic tail. Particles moving way faster than average. Now, let's go back to the exosphere. This region is blasted by the sun's extreme ultraviolet radiation, heating it to over 600 degrees Celsius. The particles here are zipping around at incredible speeds. But even then, the asterisk average particle isn't nearly fast enough to escape Earth's gravity. But what about those speed demons in the energetic tail? That's the secret to Jeans escape. In that superheated, ultra-thin layer of air, a tiny fraction of the lightest gas particles gets lucky. They get an extra jolt of energy from the sun, pushing them into that high-velocity tail. For a split second, their random, chaotic movement happens to point straight up, away from the planet. And in that same moment, their speed crosses the magic number, 11.2 kilometers per second. Poof. They're gone. They slip past the point of no return and sail off into space. The atmosphere below then sends up another particle to take its place, and the whole process repeats. It's a slow, relentless evaporation of a planet. But here's the key. Jeans escape is incredibly picky. It almost exclusively affects the lightest elements. Think of it like this. With the same amount of energy, you can throw a tennis ball much faster than a bowling ball. It's the same principle. At the same temperature, light atoms like hydrogen and helium move much faster than heavy molecules like nitrogen or oxygen. Hydrogen, with an atomic mass of just 1, is the easiest to accelerate to escape velocity. Helium, with a mass of 4, is a distant second. For comparison, molecular nitrogen, which is 78% of our air, has a mass of 28. Oxygen is 32. For these heavyweights, reaching escape velocity just by being hot is practically impossible on Earth. The number of oxygen molecules that would naturally be moving at 11.2 kilometers per second is so small it's basically zero. This is why the invisible wind is mostly bleeding hydrogen. And the numbers are huge. Every second, Earth loses about 3 kilograms of hydrogen gas. That's over 250,000 kilograms a day. At the same time, we lose a much smaller amount of helium, about 50 grams per second. Now, that sounds like a lot. And it is. But we have to remember the sheer scale of our atmosphere, which has a mass of over 5 quintillion kilograms. The amount we lose each day is like taking a single drop of water out of an entire ocean. It's a measurable leak, but it's not a catastrophic failure. Our planet's gravity is just too strong, and our main atmospheric gases are too heavy for this slow heist to ever truly hurt us. But this slow leak is just one of the ways the sun tries to pull our planet apart. There are other, more subtle, and in some cases, more violent methods at play. The sun's other weapons. While Gene's escape is the slow, grinding engine of atmospheric loss, it's not the only tool in the sun's arsenal. The star we depend on for life is also the source of other, sneakier escape mechanisms, processes that turn chemistry and magnetism against us. First, there's a process called photochemical escape. This isn't about gentle heating. This is a targeted, energetic attack. It starts with high-energy photons from the sun, like extreme ultraviolet light and X-rays. When one of these potent photons strikes a molecule in the upper atmosphere, it doesn't just warm it up, it can shatter it. Take a molecule of carbon dioxide, CO2. A high-energy photon can slam into it with enough force to break its chemical bonds, splitting it into carbon monoxide and a highly energized oxygen atom. In that violent split, the photon's energy becomes kinetic energy. The fragments fly apart like shrapnel. If that oxygen atom happens to be shot upwards with enough force, it can be launched directly into space, even though it's a relatively heavy atom. This isn't about being in the hot tail of a group. This is a single, explosive event that hands a particle a one-way ticket out of here. On modern Earth, this is a pretty minor contributor to atmospheric loss. Our gravity is just too strong. But on other worlds, or in Earth's distant past when the young sun was throwing a much more intense tantrum of UV radiation, this process was a major player in deciding a planet's fate. It's a good reminder that sunlight isn't just warmth. It's cosmic radiation with the power to chemically dismantle our atmosphere from the top down. The second of the sun's other weapons is maybe the most surprising. The polar wind. We think of Earth's magnetic field as our great protector, a planetary shield. And mostly, it is. But in a weird twist of physics, that very shield also opens up two back doors for our atmosphere to leak out. Earth's magnetic field looks like a giant bar magnet, with field lines looping out from the South Pole and back in at the north. These closed loops form a bubble around our planet, the magnetosphere, that deflects the solar wind. But right at the magnetic poles, the field lines aren't closed. They're open, stretching out from the planet like two huge, invisible funnels that connect directly to interplanetary space. In these polar regions, charged particles from our upper atmosphere, ions, can get snagged on these open magnetic field lines. Instead of being trapped by gravity, they get guided along these lines like they're on a magnetic highway, flowing away from the planet. This steady outflow of plasma is what we call the polar wind. It's not about achieving escape velocity with raw speed. It's about being escorted out of town along a magnetic expressway. The polar wind is responsible for about 10 to 15% of our hydrogen loss, but its most important job is getting rid of helium. For this noble gas, the polar wind is the main escape route. Without this magnetic highway, the helium that's constantly being produced by radioactive decay deep inside the Earth would just build up in our atmosphere over billions of years. So in a strange way, this leak is also a necessary release valve. It shows just how complex our relationship is with our own magnetic field, a shield that protects us almost everywhere, but also a channel that bleeds us at the poles. A postcard from a dead world. The Martian tragedy. For billions of years, Mars has been sending us a warning. It's written in the language of rust-red dust and barren, frozen plains. It tells the story of a world that lost the cosmic tug of war, a planet bled dry by the invisible wind. The story of Mars isn't just about another planet. It's the story of Earth's ghost. Today, Mars is a shadow. Its atmosphere is less than 1% as thick as Earth's, a pitifully thin blanket of carbon dioxide totally incapable of holding onto heat or keeping water liquid. But we know it wasn't always like this. Orbiters have mapped vast, dried-up river deltas. Rovers have driven across ancient lake beds. Early Mars, over 3 billion years ago, was warmer and wetter. It had a thick atmosphere, flowing rivers, and maybe even a northern ocean. So, what went wrong? Where did all the air go? Mars's fate was sealed by a deadly 1-2 punch. It's too small, and it lost its shield. At only about half the size of Earth, Mars has a much weaker gravitational grip. Its escape velocity is a mere 5 kilometers per second, less than half of ours. From day one, this meant it had a much harder time holding on to its atmosphere. It was born with a disadvantage. But the mortal blow came when its internal dynamo died. Like Earth, early Mars had a molten iron core that generated a global magnetic field. This shield would have protected its young atmosphere from the sun's most destructive force, the solar wind. But because Mars is small, its inside cooled down much faster than Earth's. As the core solidified, the dynamo sputtered out, and the planet's magnetic shield vanished. This left the young, vulnerable Martian atmosphere completely exposed to the direct, unrelenting blast of the solar wind, a supersonic stream of charged particles blowing off the sun. Without a magnetosphere to deflect it, the solar wind began to violently strip the Martian atmosphere away. This wasn't a slow leak. This was atmospheric erosion on a catastrophic scale. One process is called sputtering. Think of the solar wind as a sandblaster. High-energy particles from the sun slammed into the upper atmosphere of Mars, physically knocking atoms and molecules right out into space. Another, even more effective process, is ion pickup. As the solar wind swept past Mars, it would knock electrons off atmospheric particles, turning them into charged ions. Once charged, they could be picked up by the magnetic field carried within the solar wind and just stolen, carried away from the planet. For years, this was the leading theory. But the smoking gun, the definitive proof of Mars's atmospheric murder, came from NASA's MAVEN mission. MAVEN arrived at Mars in 2014 to figure out exactly how the planet lost its air and water. And it found what scientists expected. MAVEN has literally watched, in real time, as atmospheric ions flow away from the planet, caught in the grip of the solar wind. During solar storms, it's seen the rate of atmospheric loss spike dramatically, showing just how vulnerable the planet is. But maybe the most elegant evidence is in the air that's left. Scientists analyzed the isotopes of elements in the Martian atmosphere. Isotopes are just versions of an element with slightly different weights. For example, there's normal hydrogen, and then there's a heavier version called deuterium. As an atmosphere escapes, the lighter isotopes get away more easily. Over billions of years, this leaves the remaining air enriched in the heavier stuff. And that is exactly what we find on Mars. The ratio of heavy hydrogen to normal hydrogen is way higher than it is on Earth, providing a clear chemical fingerprint of massive atmospheric loss. It's the forensic evidence of a multi-billion-year-old crime scene. Mars didn't just freeze, its atmosphere was stolen. The water either escaped to space or froze underground. The result is the cold, desert world we see today, a postcard from the edge, a chilling testament to what happens when a planet's defenses fail. Fortress Earth, our planet's defenses. The story of Mars is a pretty sobering tale. It really makes you ask, why did we make it? Why did Earth survive the same solar onslaught that condemned its neighbor? The answer is that Earth, through a mix of good luck and good physics, is a fortress. It has two main defenses that have let it win the cosmic tug-of-war for over 4 billion years. The first, and most obvious defense, is gravity. It's the foundation of our resilience. Being so much more massive than Mars gives us a much deeper gravity well and that high escape velocity of 11.2 kilometers per second. This simple fact changes everything. It raises the bar for every escape mechanism. For a hydrogen atom to escape, it needs way more energy than it would on Mars. Our gravity is a powerful anchor, holding our atmosphere in a tight embrace. While Mars's gravity was a chain-link fence, Earth's is a fortress wall. But gravity alone wouldn't have been enough. Without our second-grade defense, Earth would have eventually suffered the same fate as Mars, just more slowly. That second defense is our planetary force field, the magnetosphere. Deep inside our planet, the churning of a molten iron core acts as a giant electrical dynamo, generating a powerful, global magnetic field that extends tens of thousands of kilometers into space. This is our primary shield against the solar wind. When the solar wind approaches Earth, it doesn't just slam into our atmosphere. Instead, it hits our magnetic field first. The magnetosphere deflects the flow of charged particles, parting them like the bow wave of a ship cutting through water. It creates a protected cavity where our planet can exist, forcing the vast majority of those deadly, atmosphere-stripping particles to flow harmlessly around us. This is the crucial difference. Where Mars's atmosphere stood naked before the solar wind, ours is sheltered. The sputtering and ion pickup that devastated Mars are mostly non-issues for Earth. The solar wind just can't get a good grip. Of course, the shield isn't perfect. We saw that with the polar wind. And during intense solar storms, some particles do get through, especially near the poles, where they light up the atmosphere and create the aurora. The aurora borealis and australis are beautiful, but they're also the visible evidence of a battle, the sparks flying as our magnetic shield repels a solar assault. So, Fortress Earth stands firm because of this powerful 1-2 punch. Immense gravity holding our air down, and a persistent magnetic field shielding it from the sun. It's this combination that has allowed our planet to keep its atmosphere, to keep its oceans liquid, and ultimately, to become a cradle for life. We live in an oasis maintained by the powerful, dynamic engine churning deep beneath our feet. The Cosmic Habitability Test. Venus and Titan. The contrast between Earth and Mars is a powerful lesson, but to really get the full picture, we need to look at some other neighbors. The solar system has other worlds with atmospheres, and each one tells a unique story. Two of the most fascinating are Venus, our so-called twin, and Titan, Saturn's giant moon. First, Venus. In many ways, Venus is Earth's twin. It's about the same size and mass, with almost identical gravity. And yet, it's a hellscape. Its atmosphere is 90 times thicker than Earth's, creating a runaway greenhouse effect that bakes the surface to over 460 degrees Celsius. But here's the puzzle. Like Mars, Venus has no global magnetic field. So why wasn't its atmosphere stripped away? The answer seems to be that while Venus lacks a magnetic shield, its sheer size gives it a strong gravitational anchor, much like Earth's. But more importantly, Venus started with and likely kept producing a colossal amount of gas through extreme, prolonged volcanism. While the solar wind does strip away Venus's atmosphere, it's like trying to drain an ocean with a bucket. The amount of air is so enormous that the loss rate just doesn't make a big enough dent. The thick atmosphere even creates its own weak, induced magnetosphere, as it interacts with the solar wind, offering a little bit of protection. Venus shows that gravity and a huge gas supply can be a formidable defense, even without a magnetic shield. Now let's journey out to Saturn's largest moon, Titan. This place defies all expectations. It's smaller than Mars, its gravity is feeble, and it should be an airless, frozen rock like our own moon. And yet, it has an atmosphere that's 1.5 times denser at the surface than Earth's. How is that possible? The secret is simple. It's really, really cold. Orbiting Saturn, nearly 10 times farther from the Sun than Earth, Titan's surface is a frigid -179 degrees Celsius. At those temperatures, the molecules in its nitrogen-rich atmosphere are incredibly sluggish. They just don't have the energy to move fast enough to escape, even from Titan's weak gravity. The Sun is too distant and weak to kickstart any significant atmospheric leak. On top of that, Titan spends most of its time orbiting deep inside Saturn's colossal magnetosphere, which acts as a part-time shield. Titan perfectly illustrates the third critical variable: distance from the star. Mars was too small and lost its shield. Venus had the size but was choked by its own massive atmosphere. Earth is in the Goldilocks zone in every respect: the right size, the right shield, and the right distance. And Titan shows us that even a small world can keep a thick atmosphere, as long as it stays cold enough. We started this journey with the fact that our planet is constantly leaking into space. We've traveled to the edge of our own atmosphere and then across the solar system to see what happens when planets lose this celestial battle. We've seen the slow, patient heist of genes escape, the chemical demolition of sunlight, and the strange magnetic funnels of the polar wind. We've stood on the rusted plains of Mars, a planet that shows us exactly what happens when a world's defenses fail. And in doing so, we've come to understand the true nature of Fortress Earth. We see now how our planet's gravity holds our air in place, and how the engine in our core generates a shield that fends off the sun. We now understand that the 3 kilograms of hydrogen we lose every second isn't a sign of doom, but just a whisper from a cosmic battle our world is winning. Our trip to Venus and Titan shows there's no single formula for a habitable world. A planet's fate is written in a complex language of mass, magnetism, chemistry, and distance. Earth isn't just in the right place. It is the right kind of place. So the next time you step outside and feel the wind on your face, or just take a deep breath, remember the invisible wind. Remember the silent, unending war being fought high above your head. And remember that we live not just on a planet, but inside a fortress of gravity and magnetism that has protected this fragile blue oasis and allowed life to flourish in the vast, indifferent darkness of space. If this journey to the edge of our world sparked your curiosity, consider subscribing to see where we go next. We are literally throwing Earth into space. Every year, we humans put on the most spectacular, most audacious fireworks display in history. We gather up metal, electronics, and incredibly complex machinery, pack it all onto the tip of a controlled explosion, and blast it right off the face of the planet. We are, quite literally, throwing chunks of Earth into space. Thousands of tons of our planet, meticulously crafted and then violently ejected into the void. And as you watch that pillar of fire climb, pushing against the immense gravity of our world, a perfectly logical thought might cross your mind. With all this stuff we're flinging into the cosmos, surely, the Earth has to be getting lighter, right? Piece by piece, rocket by rocket, we must be shedding some weight. It's just common sense. But what if I told you that the roar of our rockets and the glitter of our new satellite constellations are barely a whisper in a much larger, much stranger cosmic conversation? What if all our monumental efforts to leave this planet are completely dwarfed by invisible forces that are changing our world's mass every single second? The truth is, while we're all looking up at the fire, the real story of Earth's weight is happening silently, all around us. And it's a story that is far more bizarre, and far more profound, than you could ever imagine. Every single year, we launch thousands of tons of material off our planet, basically tossing Earth into the cosmos, one piece at a time. In recent years, the amount of mass we've launched has skyrocketed. In 2024, the total mass hoisted into orbit topped 9 million kilograms, that's nearly 2,000 tons in a single year. So you'd think the Earth is getting lighter. It has to be. Well, the truth is far stranger. While our rockets are roaring into the void, the biggest changes to our planet's mass are happening silently, all around us, every second of every day. And they tell a completely different story. To solve this planetary mystery, we first need to confront the myth of our own making, the idea that we're the star of the show. So let's run the numbers on ourselves and see just how big of a dent we're really making. The myth: our human footprint. When we think about changing the planet's mass, our minds jump straight to the most dramatic example: space travel. It feels significant. It looks significant. Companies like SpaceX are a huge driver of this, launching dozens upon dozens of times a year. We've seen a massive ramp up in activity, with 2024 averaging nearly one launch attempt every 34 hours. And this isn't just about a few big, custom-built science missions anymore. We're now building mega constellations of satellites, like SpaceX's Starlink, which now has a staggering number of satellites, well over 900 as of early 2026, providing internet from above. But if we add up all the mass from all the rockets and satellites we've ever sent on a one-way trip to escape Earth's gravity entirely and journey into deep space, the number is shockingly small. It's estimated to be around 65 tons per year. That's it. To put that in perspective, that's about the weight of a single M1 Abrams tank, or maybe 10 big elephants. All of humanity's yearly efforts to send probes to Mars, Jupiter, and beyond amount to subtracting 10 elephants from a planet that weighs nearly 6 sextillion tons. But wait, you say. What about everything else? The thousands of satellites that don't leave forever? What about the International Space Station? That's a great question. The total mass of all objects currently orbiting Earth is more than 15,800 tons. That's a lot more than 65. However, that mass hasn't actually left the Earth system. It's just been lifted up. It's still bound by Earth's gravity, a part of our planetary system, just like the Moon is. It's like picking up a rock and holding it over your head. You've changed its position, but you haven't changed the combined weight of you and the rock. For an object in orbit, its mass is still counted as part of Earth's total mass. Now, there is a nuance here. What goes up often comes down. Satellites in low Earth orbit have a limited lifespan. Drag from the wispy outer edges of our atmosphere slowly pulls them down. A few Starlink satellites are already re-entering the atmosphere every day. But they don't come back in one piece. They burn up, vaporizing into a haze of tiny metallic particles that mostly linger in the upper atmosphere. So, does that count as returning the mass? Yes and no. The atoms are still within our atmosphere, but their form and location have changed. From a planetary bookkeeping perspective, though, they haven't gone anywhere. They're still here. So, if launching things into space is our most obvious way of throwing Earth into space, and it amounts to a rounding error, what about our other activities? We are a civilization of builders. We move mountains, literally. Think about mining. Every year, humanity digs up billions of tons of coal, iron ore, and other minerals. But here's the key. We are just moving this mass around. We dig iron ore out of a pit in Australia, ship it to a factory in China, turn it into a car, and then sell that car in Germany. The atoms have been rearranged and reformed, but they're still on planet Earth. They haven't been lost. They've just been redistributed. It's like shifting furniture around in a very, very large house. The weight of the house doesn't change. Then there's the burning of fossil fuels. This one is fascinating because it feels like a real transformation. We take a solid, like coal, or liquid, like oil, and burn it. This act of combustion turns that solid carbon into a gas, carbon dioxide. We release billions of tons of CO2 into the atmosphere every year. So, are we lightening the load by turning solids into gas? Not really. It's the same story, redistribution. The carbon atom that was in a chunk of coal is now bonded with 2 oxygen atoms from the atmosphere, and that CO2 molecule is just floating around in the atmosphere. The mass is still here. In a strange twist, by adding energy to the Earth system through global warming, some calculations suggest this actually adds a tiny amount of mass to the planet each year, about 160 tons based on Einstein's famous equation, E=mc². It's a mind-bendingly small number, but it goes in the asterisk opposite direction you might think. So let's take stock. Our most powerful rockets? A negligible annual mass loss. Our vast industrial operations? Just planetary scale interior decorating. The myth that our activity is dramatically slimming down the planet just doesn't hold up. Our impact, as impressive as it looks, is a distraction from the real forces at play. The turn, putting our impact in perspective. Okay, so we've established that our efforts to launch stuff off the planet are, on a planetary scale, almost comically small. A few dozen tons on escape trajectories each year is basically nothing. And every good mystery has a moment where the detective realizes the obvious suspect couldn't have done it. This is that moment. The total mass of the Earth is about 5,972 sextillion metric tons. That's a number so colossal our brains aren't equipped to comprehend it. Let's try an analogy. Imagine the entire mass of the Earth is represented by all the sand on all the beaches and in all the deserts in the entire world. Every single grain. Now, the amount of mass we humans permanently eject from Earth in a year, our deep space probes and rovers, is equivalent to picking up a single grain of that sand and tossing it into the wind. One single grain. That's it. That's our contribution. Seeing it this way, it's clear we've been looking in the wrong place. If our roaring engines aren't the main drivers of Earth's changing mass, then what is? The answer isn't on our launch pads. The real clues are in the silent, invisible processes that have been shaping our planet for billions of years. We have to zoom out, from the human scale to the cosmic scale. We need to look up, not at our own creations, but at the space our planet travels through. And we need to look closer at the very air we breathe. The real story of Earth's weight is a cosmic balancing act, a celestial ledger with a massive income column and an even bigger expenses column. And our activities don't even qualify as a footnote. So, let's look at the first, and most significant, entry on the credit side. The constant, unending rain of stuff from outer space. The reality, Part 1: The gain from above. While we've been busy launching a few thousand tons into orbit, our planet has been quietly and effortlessly accumulating mass from the cosmos on a scale that dwarfs our efforts. Every single day, Earth is showered with dust from space. This isn't the dust on your bookshelves. This is cosmic dust, primordial leftovers from the formation of our solar system. It's the dust of comets and the pulverized remains of asteroids. Our solar system isn't empty. It's filled with a fine haze of this material, and Earth is constantly plowing through it. So how much are we talking about? Scientists use everything from satellites and radar to collecting micrometeorites in Antarctica to figure this out. Piecing it all together, they arrive at a staggering figure. Every year, Earth gains about 40,000 metric tons of mass from this incoming space dust. Think about that for a second. 40,000 tons. Every single year. Let's try to picture that. A modern aircraft carrier weighs about 100,000 tons. So the cosmic dust falling on Earth every 2.5 years is like the mass of one of the largest warships ever built, appearing out of thin air and spreading itself across the globe. Or think of it this way. A big African elephant weighs about 6 tons. 40,000 tons is the equivalent of nearly 7,000 elephants worth of mass being added to our planet, not with a thundering stampede, but with the silent settling of microscopic particles. This constant rain is the single biggest factor in Earth's mass increase. It's been happening every day for 4-5 billion years. In a very real sense, the planets are still being built, grain by microscopic grain. Most of these particles are tiny, smaller than a grain of sand. As they hit our upper atmosphere, they burn up, creating the streaks of light we call shooting stars. The bigger ones survive and land as micrometeorites. If you were to take a powerful magnet and drag it through the gunk on your roof, you would, with some luck and a microscope, almost certainly find a few of these tiny spheres of cosmic iron. So, while we're spending billions to throw a few tons of our planet outwards, the universe is casually tossing 40,000 tons of itself back at us, for free. It's a humbling thought. This is the income side of the ledger. A steady, massive gain. But income is only half the story. To get the net change, we have to look at the expenses. And this is where the story takes its strangest turn, into the silent, relentless escape of our planet's own substance into the void. The reality, Part 2: The Invisible Escape. We've now accounted for the single biggest source of mass gain. A perpetual, 40,000 ton per year deluge of cosmic dust. So, Earth must be getting heavier, right? It seems logical. But this is where the mystery deepens, because there's another, even larger force working in the opposite direction. Our planet, it turns out, is leaking. This isn't a leak you can plug. It's happening at the very top of our atmosphere in a process called atmospheric escape. And it is relentlessly stripping our world of its mass, molecule by molecule. The main culprits are the two lightest and nimblest elements: hydrogen and helium. Picture the top of our atmosphere, the exosphere. The air there is incredibly thin. The gas particles are whizzing around, and some, just by chance, get a powerful kick from a collision that sends them flying upwards. For heavy gases like oxygen and nitrogen, Earth's gravity is an unbreakable leash. They always fall back down. But hydrogen and helium are different. They're the featherweights. If a particle of hydrogen or helium at the top of the atmosphere gets moving fast enough, it can actually reach escape velocity about 11.2 kilometers per second. At that speed, Earth's gravity can't hold on, and it just coasts away, forever. So where does this escaping hydrogen come from? A lot of it starts as water vapor, H2O. When powerful ultraviolet sunlight strikes a water molecule in the upper atmosphere, it can break it apart. The heavier oxygen atom sticks around, but the two light hydrogen atoms are now free to be kicked out into space. Helium's story is even more interesting. Most of the helium on Earth is created by the slow radioactive decay of elements like uranium and thorium deep in the Earth's crust. For billions of years, tiny amounts of helium have percolated up through the rock, into the atmosphere, and eventually to the top, where they too can escape. The planet is literally exhaling the byproducts of its own radioactivity. So what does this invisible leak amount to? The numbers are staggering. Scientists estimate that Earth loses about 95,000 metric tons of hydrogen every single year. On top of that, we lose another 1,600 tons of helium. Let's put that in context. Our gain from space dust was 40,000 tons. Our loss of just these two gases is over 96,000 tons. That means every year, we lose more than twice as much mass to escaping gas than we gain from cosmic dust. It's an invisible, silent, and continuous process. No roaring engines, no pillars of fire. Just the ceaseless dance of atoms at the edge of space. This is the single biggest factor in our planet's annual mass change. It's not our rockets. It's not asteroids. It is the quiet, unstoppable flight of the lightest elements from the top of our own sky. The grand accounting and the final verdict. We started with a simple question. Are we making the Earth lighter by launching rockets? We've journeyed through cosmic dust, atmospheric physics, and planetary science to find the answer. Now, it's time for the final accounting. On the gain side of the ledger, we have one main entry. Cosmic dust. An influx of approximately plus 40,000 metric tons per year. On the loss side, we have two dominant entries. Hydrogen escape. A constant leak of approximately minus 95,000 metric tons per year. Helium escape. A smaller leak of approximately minus 1,600 metric tons per year. And then we have the much smaller factors we discussed. Human spacecraft escape. A loss of about minus 65 tons per year. Radioactive decay. A loss of about minus 16 tons per year. Global warming. A gain of about plus 160 tons per year. Alright, let's tally up the final score. We have a total gain of roughly 160 tons. We have a total loss of roughly 681 tons. When we do the math, we get the final verdict. Every year, planet Earth experiences a net mass loss of roughly *56,000 metric tons. So, the answer is yes. The Earth is getting lighter. But it has almost nothing to do with us. Our dramatic, fiery launches are a tiny, insignificant footnote in this grand, planetary process. The real reason our planet is shedding weight is because it is quietly, invisibly, and relentlessly leaking its lightest gases into the infinite void of space. So, we aren't the masters of Earth's weight. We are passengers on a colossal, leaking, dust-collecting spaceship that has been navigating the cosmos for billions of years. Our planet is a dynamic system, breathing in the remnants of ancient stars and exhaling its own atoms into the void. A loss of 56,000 tons a year is utterly insignificant to the planet's future. It would take trillions of years for this process to make a major difference, a timescale far longer than the remaining life of our sun. The real lesson here isn't the number itself, but the change in perspective. We started with an act of human power, the rocket launch, and ended with a lesson in cosmic humility. It reminds us that for all our technology, we are subject to natural forces that operate on scales we can barely comprehend. The story of Earth's mass isn't about human achievement. It's about physics. The next time you see a shooting star, remember what you're seeing. It's the universe making a deposit into Earth's mass account, a tiny piece of the 40,000 tons our planet will gain this year. And when you think of the vast blackness of space, remember it's the destination for the thousands of tons of our own atmosphere that will silently slip away, atom by atom. We live on a world that is constantly in flux, a world that is both gathering and losing itself to the cosmos. And that is a far stranger, and more wonderful, story than just throwing a few rockets into the sky. If you enjoyed this journey into the strange science of our planet, consider subscribing for more. And let us know in the comments, what other cosmic mysteries should we unravel next? We are changing the spin of the Earth. You know how a spinning top, when it's perfectly balanced, spins fast and true on one single point. It's a hypnotic, perfect dance of physics. But what happens if you add a tiny drop of glue to one side? Just a minuscule amount of extra weight. That perfect spin starts to falter. It wobbles. The smooth rotation becomes a lurching, erratic gyration. Now, what if I told you that exact same thing is happening right now, not to a toy, but to our entire planet? What if I told you that we, humanity, are the ones adding that drop of glue? Except it's not a drop. It's trillions of tons of mass, being moved from one part of the world to another, every single year. We are fundamentally altering the balance of our planet. And as a result, we are changing the very spin of the Earth. This isn't a theory or a prediction for some distant future. It's a measured, documented, and frankly, startling reality. And it's happening because of two major forces. One you know about, and one you probably don't. The first is the colossal melting of our planet's ice sheets. The second, and perhaps more shocking, is something many of us do every day without a second thought: pumping water from deep within the ground. This story isn't just about abstract physics. It's about how our collective actions are powerful enough to physically move the axis our world spins on. It's about how we're subtly altering the length of our days and forcing ourselves to question the very definition of time. We have become a geological force, a species capable of nudging a quintillion-ton planet off balance. And the story of how we figured this all out is one of the most profound scientific detective stories of our time. The problem: a planet out of balance. To understand how a planet gets knocked off kilter, you first have to appreciate its incredible, delicate balance. Earth isn't a perfect, static sphere. It's a dynamic system, with mass constantly in motion. Deep inside, molten rock churns. On the surface, oceans shuttle water across basins, and the atmosphere shifts its weight with the weather. These natural movements have always caused the Earth's rotational axis, that imaginary line through the North and South poles, to drift and wobble a tiny bit. For most of history, the poles wandered by a few inches a year, pushed and pulled by these immense, natural forces. Think of the Earth as a giant, spinning figure skater. When the skater pulls their arms in, they spin faster. When they extend their arms out, they slow down. This is a fundamental law of physics called the conservation of angular momentum, and it applies to our planet, too. If you move a huge amount of mass from the poles, close to the axis of rotation, like the skater's torso, and spread it toward the equator, further from the axis, like the skater's extended arms, the planet's rotation has to slow down. For millennia, the Earth's natural checks and balances kept this wobble in check. But then came the 20th century, and humanity's footprint began to grow exponentially. We built massive cities, we farmed on an industrial scale, and our appetite for energy became insatiable. We know the consequences all too well, from rising temperatures to a changing climate. But scientists tracking the precise location of the poles noticed something else, something strange. Around the mid-1990s, the direction of the polar drift, which had been meandering south, took an abrupt turn and began heading east. Not only that, but the speed of the drift accelerated dramatically. Between 1995 and 2020, the average speed of this polar wander was nearly 4 times faster than it was between 1981 and 1995. The planet was wobbling more, and faster, than it had in recorded history. Since 1980, the position of the poles has moved by about 4 meters. The question was, why? What on earth could be powerful enough to change the wobble of our planet so suddenly? The answer was hiding in plain sight, and it would reveal the true scale of our impact. The two main culprits were the melting of ice and the movement of groundwater. And the evidence was undeniable. The ice factor, glaciers, gravity, and a slower Earth. The most visible driver of this planetary imbalance is the melting of Earth's great ice sheets in Greenland and Antarctica. These aren't just big glaciers. They are continent-sized reservoirs of frozen water, so immense they literally warp the Earth's crust beneath them. For thousands of years, they sat at the poles, vast, stable weights anchoring the planet's spin. Now, they are pouring into the ocean at a terrifying rate. A January 2024 study gave us a shocking new number. Greenland is losing an average of 30 million tons of ice every single hour. That's not a typo. Every hour. To put that in perspective, it's like a fleet of 200,000 fully loaded aircraft carriers worth of ice vanishing into the sea every 60 minutes. Another recent NASA study found that Greenland has actually shed about 20% more mass over the last 4 decades than previously thought, a difference of over 1 trillion tons. In northeast Greenland, one glacier alone has thinned by more than 160 meters since 1998, melted from below by warm ocean water. The scale of this loss is almost beyond comprehension. Between just 1992 and 2020, Greenland lost nearly 400 billion tons of ice. And this is where that figure skater analogy becomes critical. All this ice, once held tightly at the poles, is melting and flowing into the world's oceans. The oceans naturally bulge at the equator because of Earth's spin. So, we are taking trillions of tons of mass from the poles and moving it to the equator. We are forcing the figure skater's arms to extend. The result is inevitable. The Earth's rotation is slowing down. A 2024 study in the journal Nature confirmed this exact effect, highlighting that the rapid melting of polar ice is acting as a brake on the planet's spin. It's a tiny change, just milliseconds added to a day, but it's a direct, physical consequence of our warming world. The sheer weight of melted ice is powerful enough to alter our planet's angular momentum. But here's the twist. While the melting ice is a huge factor, scientists realized it couldn't fully account for the polar wander they were seeing. When they ran the models with just ice melt, the numbers didn't quite add up. There was a missing piece, another human-driven force moving a staggering amount of mass. This hidden factor was the key to the whole mystery. The hidden culprit: pumping water from the depths. Imagine a resource hidden beneath our feet, a vast, silent ocean saturating the rock and soil. This is groundwater, and it makes up nearly all of the planet's liquid freshwater. For most of history, it was untouchable. But with powerful pumps, we began to tap into it, first as a backup, and now as a primary source of water for our farms, industries, and cities. We've been drilling wells and pumping this ancient water to the surface on a scale so massive that it has become the other great driver of Earth's changing spin. A groundbreaking study in Geophysical Research Letters delivered the stunning conclusion. Between 1993 and 2010 alone, humanity pumped an estimated 150 gigatons of groundwater from the Earth's crust. A gigaton is a billion tons. That number is so large it's hard to wrap your head around. It's the weight of more than 5.5 million Empire State Buildings. And where does all that water go? Once used, it evaporates, enters the water cycle, and overwhelmingly, ends up in the oceans. This is the crucial part. We are taking mass that was locked inside the continents and moving it into the oceans. This has an effect remarkably similar to melting glaciers. The two main areas of groundwater depletion are Western North America and Northwestern India, both in the Earth's mid-latitudes. By removing mass from these areas and transferring it to the oceans, which bulge at the equator, we are once again shifting weight away from the Earth's rotational axis. The impact is astonishing. Researchers calculated that this pumping of groundwater was responsible for shifting the Earth's axis by nearly 80 centimeters, or about 31.5 inches, eastward in just that 17-year period. It accounted for a drift of about 1.7 inches per year. When scientists first tried to model the polar wander, their results were off. They only matched the real-world observations perfectly when they included those 150 gigatons of pumped groundwater. It was the smoking gun. Kee-Wheean Seo, the geophysicist who led the study, put it plainly. Our study shows that among climate-related causes, the redistribution of groundwater actually has the largest impact on the drift of the rotational pole. Think about that. As dramatic as the melting of Greenland is, the invisible act of pumping water from the ground has had an even greater effect on physically tilting our planet. As NASA geophysicist Surendra Adhikari said, the very way the planet wobbles is impacted by our activities. It is, in a way, mind-boggling. Every time a crop is watered with pumped groundwater, every time we turn on a tap fed by an aquifer, we contribute, in some tiny way, to this global shift. The collective weight of our thirst is tilting the world. The Gravity Detectives. The GRACE mission. So how do we know all this for sure? How can you possibly weigh a melting ice sheet from space or detect invisible groundwater buried deep in the Earth? The answer lies with one of the most ingenious satellite missions ever conceived. GRACE, the Gravity Recovery and Climate Experiment. Launched in 2002, GRACE was a pair of twin satellites flying in formation, one trailing the other by about 220 kilometers. They had no cameras or radars. Their only job was to measure one thing with exquisite precision: the distance between them. A microwave ranging system allowed them to detect changes in that distance down to the width of a human hair. The principle is beautifully simple. Gravity is slightly stronger over areas with more mass. As the lead satellite flew over a region of higher mass, like a thick ice sheet, it would be pulled forward just a tiny bit, increasing the distance to the trailing satellite. As it passed and the second satellite felt the same pull, the gap would shrink again. By tracking these tiny fluctuations, month after month, the GRACE satellites created an entirely new kind of map. A map of Earth's changing gravity field. For the first time, scientists could literally watch water move around the planet. When they aimed this gravity vision at Greenland and Antarctica, the signal was unmistakable. A growing gravity deficit over the poles, a clear sign of massive ice loss. GRACE was weighing the ice sheets from orbit. But the real surprise came when they looked at the continents. Over regions like northern India and the American West, they saw the same gravity deficit. There were no glaciers there. What they were seeing was the depletion of those vast underground aquifers. GRACE was weighing the groundwater from space, providing the hard data that proved 150 gigatons had been removed. It was the final puzzle piece. The original GRACE mission ended in 2017, but its successor, GRACE Follow-On, launched in 2018 and continues this critical work today. These gravity detectives have given us an unprecedented view of our planet, proving, in undeniable terms, that our actions have real, planetary-scale consequences. The consequences. A question of time. So, the Earth is wobbling more, its axis is shifting, and its spin is slowing. What does that actually mean for us? The most direct consequence is on our very definition of time itself. Our modern world runs on atomic clocks. They are the astoundingly precise backbone of everything from GPS to the internet. The problem is, our ultra-precise atomic time, UTC, is now running slightly ahead of time based on the Earth's slowing rotation, UT1. To keep them in sync, the world's timekeepers invented the leap second. Since 1972, they have occasionally added an extra second to the clock, where it would read 23 hours 59 minutes and 59 seconds, then 23:59:60, before midnight. So far, 27 leap seconds have been added, all to let the slowing Earth catch up. But now, things have gotten weird. Alongside the long-term breaking from melting ice, other factors, like flows in the Earth's liquid core, have actually caused the planet's rotation to temporarily speed up. This led to the shortest day ever recorded in the atomic clock era in June 2022. For a while, scientists were seriously discussing the need for the world's first negative leap second, having to skip a second to let our clocks catch up with a faster Earth. This is where our story comes full circle. A March 2024 study by geophysicist Duncan Agnew found that the slowdown caused by ice melt is so significant that it has counteracted the core's influence. It has delayed the potential need for that negative leap second from around 2026 to at least 2029. In other words, our impact on the climate is now directly interfering with global timekeeping decisions. This whole chaotic situation has become a massive headache for the computer systems that run our world, so international bodies have voted to get rid of the leap second by 2035. But the debate itself shows just how much these millisecond changes now matter. The precise orientation of the Earth is also critical for GPS. While the current shifts can be corrected for, they represent a new uncertainty introduced into the system by us. Ultimately, the most profound consequence is one of perspective. The fact that our collective actions can alter the planet's rotation is the ultimate proof that we are living in the Anthropocene, the geological age defined by human influence. We're no longer just passengers on this planet. We're messing with the controls. We began with a simple image, a spinning top, wobbled by a tiny weight. We end with the staggering reality that humanity has become that weight. The 150 gigatons of water we pumped, moving the planet's axis by over 2.5 feet. The 30 million tons of ice melting every hour in Greenland, putting a brake on the Earth's rotation. These are the fingerprints of a civilization with planetary scale influence. What's truly remarkable is that we are the first generation to see this happening in real time. Thanks to the ingenuity of missions like GRACE, we can weigh our impact from orbit and watch the planet's balance shift month by month. The science is no longer theoretical, it's observational. It tells us that the Earth is one deeply interconnected system. This knowledge is both unnerving and empowering. It's unnerving to think our daily lives, aggregated across billions of people, can have such a profound physical effect. But it's also empowering. If we are powerful enough to tilt the axis of our world, then we are surely powerful enough to choose a more balanced path forward. The story of Earth's changing spin is a wake-up call. It is a definitive, physical measure of our impact, a signal written into the very motion of our world. It proves we live in a time where the fate of the planetary system is inextricably linked to the choices we make. The spinning top is wobbling, and we are the ones who must decide how to steady it. The real reason Earth is lighter today than yesterday. It's a simple piece of logic. Stand in a light rain, you get a little wet. Stand in a downpour, you get soaked. It seems obvious that the longer you're out there, the more water you'll soak up. Well, the same thing should apply to our planet. Every single moment of every single day, Earth is moving through a cosmic downpour, a relentless shower of dust and debris left over from the birth of our solar system. And this isn't some gentle sprinkle. It's a constant, planetary-scale bombardment. And yet, despite all this stuff being added, our planet is actually getting lighter. Not by a lot, but by a measurable, undeniable amount. It's a paradox that just doesn't seem to make sense. How can something that is constantly being added to end up with less? It feels like trying to fill a bucket that has a hole in the bottom, only the hole is somehow bigger than the faucet. This isn't a riddle or some thought experiment. It's really happening. The Earth you're standing on right now is, in fact, lighter than the Earth of yesterday. And tomorrow, it will be lighter still. The reason for this planetary diet has nothing to do with the rocks and dust falling from the sky, and everything to do with the very air we need to survive. The truth is, our planet is leaking. It's bleeding its own atmosphere into the void of space, and it's happening faster than you can imagine. This is the story of that cosmic leak, a tale of gain and loss on an astronomical scale, and the real reason our world is slowly, silently, getting a little bit smaller. Every single day, our planet gets pelted with thousands of tons of space dust. So, the idea that the Earth could be getting lighter seems impossible. But it is. The real reason has nothing to do with what's arriving, and everything to do with what's leaving. And what's leaving is something so fundamental to our world, we rarely even think about it. It's like a ghost slipping away into the night, a silent escape happening miles above our heads. To solve this incredible mystery, we first need to understand the side of the equation that makes perfect sense: the constant, heavy rain of cosmic material our planet is soaking up. We have to appreciate the sheer scale of what Earth gains before we can truly grasp the magnitude of what it's losing. The cosmic income: what Earth gains. Imagine our solar system isn't a clean, empty vacuum, but more like a dusty, ancient attic. For 4.5 billion years, it's been filled with the leftovers of creation. Trillions of asteroids endlessly circle the sun, occasionally bumping into each other and shattering. Comets swing in from the outer darkness, their ice turning to gas and releasing vast clouds of dust and rock. This cosmic dust doesn't just stay put. It drifts. It spirals. And our planet, Earth, is plowing right through this celestial fog at a staggering 67,000 miles per hour. We are, in effect, the universe's vacuum cleaner. The material that falls onto Earth is technically called micrometeorites. These are particles often no bigger than a grain of sand. But when you're a planet-sized object moving at incredible speeds, you sweep up a asterisk lot of them. So, how do we know this? Well, scientists have gone to some pretty incredible lengths to figure it out. They've analyzed deep-sea sediments, where cosmic dust can be distinguished from our own dirt. They've even traveled to the pristine, frozen landscapes of Antarctica, where the white ice sheets act as a perfect canvas, making it easier to find and collect these tiny visitors from space. Through decades of this painstaking work, researchers have landed on an astounding number. Every single year, our planet gains mass from this cosmic dust and meteoritic material. Recent studies that involved collecting samples from Antarctica estimate that about 200 metric tons of this dust reaches the surface annually. However, many more particles burn up in the atmosphere. The total amount of material that Earth gains is often estimated to be around 40,000 metric tons per year when accounting for all sources. Let's try to wrap our heads around that number. That's like the weight of a blue whale falling from space every single day. Most of this stuff is so small that it burns up high in our atmosphere, creating the fleeting streaks of light we call shooting stars. These are the final, fiery moments of tiny rocks that have traveled millions of miles, only to vaporize and settle as invisible dust on the surface. This constant bombardment is the most obvious part of Earth's mass change equation. It's the income column in our planetary budget. And it leads to a very powerful, but wrong, idea that the Earth must be a closed system. We learn in school about the conservation of mass, that matter can't be created or destroyed. It feels natural to apply this to our planet as a whole. We think of it as a sealed terrarium, a beautiful blue marble where everything just gets recycled. So, if new material is constantly being added from space, then the total mass must go up. It's simple addition. But this is where our intuition leads us astray. The Earth is not a sealed jar. It's an open system, constantly exchanging stuff with the hostile environment of space. It has an income, yes, a very substantial one. But it also has an expense column. And it's this cosmic expense, this planetary leak, that holds the secret to why our world is getting lighter. The addition of all that cosmic material is a dramatic and powerful process, but it's completely overshadowed by something much larger, and far more subtle. The planetary expense. The Great Escape. If the gain is a fiery spectacle of shooting stars, the loss is a silent, invisible ghost. It's happening right now, high above the clouds, in the wispy, outermost layers of our atmosphere. This process is known as atmospheric escape, and it is, quite literally, our planet's air leaking away into the vacuum of space. To understand how this is possible, we need to think about gravity and speed. Everything on Earth is held here by gravity. Throw a ball, it comes down. Jump, you come down. But what if you could throw that ball so incredibly fast that it just kept going? This is known as escape velocity. For an object to break free from Earth's gravity and never fall back, it needs to be traveling at a staggering 11.2 kilometers per second. That's about 25,000 miles per hour. Nothing can casually hit that speed near the surface. But way up in the upper atmosphere, things are different. The air we breathe down here is dense and heavy. But as you go higher, the air gets thinner and thinner. The outermost layer, the exosphere, is where our atmosphere fades into the blackness of space. Down here, air particles are constantly bumping into each other. But up in the exosphere, the air is so thin that a particle can travel for miles without hitting another thing. And it's here that the great escape happens. The key players in this escape are the two lightest elements, hydrogen and helium. Think of the atmosphere as a giant party. The heavier gases, like oxygen and nitrogen, are the sluggish dancers stuck to the gravitational dance floor. But hydrogen and helium are the lightweights. They're the energetic particles bouncing all over the place. Because they're so light, they don't need as big of a push to get moving really, really fast. So where do these light gases come from? Hydrogen is mainly born from the destruction of water. High in the atmosphere, intense sunlight acts like cosmic scissors, splitting water molecules, H2O, into hydrogen and oxygen. The heavier oxygen tends to stick around, but the incredibly light hydrogen is now free. Helium has a different origin. It's born deep inside the Earth from the slow, radioactive decay of elements like uranium and thorium. Over millions of years, it seeps up through the crust and eventually makes its way into the atmosphere. Once these light gases get to the top of the hot, thin exosphere, they're ready to make a break for it. The main way this happens is through a process called thermal escape, or Jeans escape. The exosphere is incredibly hot. Temperatures can soar over 1,500 degrees Celsius, 2,700 Fahrenheit. In physics, temperature is just a measure of how fast particles are moving. Now, that's an asterisk average speed. Some particles are slower, some are average, and a tiny fraction, just by random chance, are moving much, much faster. In the blistering heat of the exosphere, the fastest moving hydrogen and helium atoms can briefly reach escape velocity. If they're heading up and away from Earth, there's nothing to stop them. They just coast away, leaving the planet forever. It's a slow, constant boiling off of the lightest parts of our air. This isn't the only way we lose atmosphere. Another process, known as the polar wind, acts like a planetary vacuum cleaner. Earth's magnetic field protects us from the solar wind, but it has weak spots at the north and south poles where the field lines are open, funneling out into space. Gas particles can get an electric charge from solar radiation, and once charged, they can be grabbed by the magnetic field and shot out along these open funnels, escaping into space. So, how much are we losing? The numbers are even more staggering than the gains. Scientists estimate that through these escape mechanisms, Earth loses about 3 kilograms of hydrogen every single second. That adds up. It's about 95,000 metric tons of hydrogen bleeding into the void every year. Helium, being a bit heavier, escapes at a slower rate, contributing a loss of about 1,600 metric tons per year. This is the great planetary expense. It's a massive, ongoing leak that has been happening for billions of years. The bottom line: a cosmic balancing act. Now we have both sides of the budget. On one side, we have the cosmic income, an estimated 40,000 tons of space dust falling onto our planet each year. On the other, the planetary expense. A silent hemorrhage of our atmosphere, amounting to roughly 95,000 tons of hydrogen and another 1,600 tons of helium annually. It's time to do the math. The calculation is stark. We gain 40,000 tons, but we lose a combined total of about 96,600 tons of gas. When you subtract the gains from the losses, you're left with a clear deficit. Every year, our planet experiences a net loss of approximately 56,600 metric tons. For simplicity, and to account for the difficulty in measuring these things precisely, scientists often round this to a net loss of roughly 50,000 metric tons per year. This is the answer to the paradox. This is the real reason Earth is lighter today than it was yesterday. The atmospheric leak is so much bigger than the cosmic dust shower that the net result is a planet on a diet. But that's not the whole story. There are a couple of other, much smaller, factors at play. Deep within the Earth, the core acts as a giant nuclear reactor, where radioactive decay releases a tremendous amount of energy. Here, Einstein's famous equation, E=mc², comes into play. When the Earth radiates that heat energy into space, it is, according to this law, losing a tiny amount of mass. This loss is remarkably small, only about 16 tons per year. There's one other factor, and it's one we created. Since the space age began, we've been launching things with enough force to escape Earth's gravity. Every satellite we send to another planet, every probe like Voyager destined to leave our solar system forever, carries a tiny fraction of Earth's mass away with it. This adds up to an estimated 65 tons of mass lost per year. So, if we add up all the losses, the hydrogen, the helium, the radioactive decay, and our departing spacecraft, we get a total loss of about 96,681 tons per year. Compared to the gain of around 40,000 tons of dust, the net loss remains firmly in that 50,000 to 60,000 ton ballpark. The conclusion is inescapable. Our planet is slowly getting lighter. So what? Why this doesn't matter? And why it does? A net loss of 50,000 metric tons a year sounds dramatic. It's like an aircraft carrier vanishing from the planet every 12 months. It's natural to hear that and feel a little worried. Is our atmosphere going to disappear? Is our planet wasting away? The answer, without a doubt, is no. To understand why, we need to deal with the truly mind-bending scale of our planet. The total mass of the Earth is about 5.97 billion trillion metric tons. That's a number so huge our brains can't really process it. Losing 50,000 tons from that total is like an 800-pound gorilla losing a single eyelash. It is so incredibly tiny that it's completely insignificant. If we kept losing mass at this rate, it would take about 120,000 trillion years for the Earth to disappear completely. For context, the entire universe is only about 13.8 billion years old. The Sun will have burned out and died long before the Earth loses even a tiny fraction of a percent of its mass. This process has zero effect on our daily lives. It doesn't affect gravity, our orbit, or the length of a day. In fact, the change is so small that scientists can't directly measure the yearly change in Earth's mass. It falls entirely within the margin of error of our best measurements. So, if it's so insignificant, why do we care? Because while it doesn't matter for the asterisk future of Earth, it matters immensely for understanding planets everywhere, including our own past. Atmospheric escape is a fundamental part of how planets evolve. The most dramatic example is Mars. Today, Mars is a cold, dry desert world with an atmosphere less than 1% as dense as Earth's. But all the evidence suggests that billions of years ago, Mars had a thick atmosphere and liquid water. It was a much more Earth-like world. So what happened? Mars suffered a catastrophic case of atmospheric escape. Being smaller than Earth, its gravity is weaker. More importantly, early in its history, Mars lost its protective global magnetic field. Without that shield, the solar wind stripped its atmosphere away over hundreds of millions of years. The very same processes happening slowly on Earth ran wild on Mars, turning a potentially habitable world into a barren wasteland. This is also critical in our search for life beyond our solar system. When astronomers find a new exoplanet, a key question is whether it can hold on to an atmosphere. A planet might be in the habitable zone, but if it's too small or unprotected, it will lose its air and water to space, making it sterile. Understanding this process is a crucial filter in our search for another living world. So, we have a clear picture. A long-term, natural process of mass loss that outweighs the gain from cosmic dust. But in the grand story of our planet, there's always another layer. And in recent decades, a new, human-driven factor has entered the equation, one that is, bizarrely, making the Earth infinitesimally heavier. That factor is climate change. It sounds strange, but it comes back to E equals mc squared. As greenhouse gases trap more of the sun's energy, the planet's total energy content is increasing. This added energy has an equivalent mass. More energy means more mass. According to scientific estimates, the energy imbalance caused by global warming may be adding the equivalent of around 160 tons of mass to the Earth every year. This creates a fascinating paradox. As our planet continues its multi-billion-year-old diet, slowly shedding its atmosphere, our civilization has inadvertently started to force-feed it energy. We are, in a weird twist of cosmic fate, temporarily making our planet heavier by trapping heat, even as its natural processes work to make it lighter. Now, to be clear, this 160-ton gain is a tiny blip. It doesn't cancel out the 50,000-ton net loss in the long run. But it's a powerful reminder that the Earth isn't a simple, static rock. It's a complex, interconnected system, where our actions can have unexpected consequences on a planetary scale. The story of Earth's changing weight is a perfect example of how science peels back our simple intuitions to reveal a much more complex and fascinating reality. We started with a paradox. A planet that's constantly being hit with space dust, but is somehow getting lighter. The solution took us from the fiery death of micrometeorites to the physics of atoms escaping gravity at the very edge of space. We learned that our planet has both an income and an expense. It gains around 40,000 tons of mass each year from a shower of cosmic dust. But it loses far more, nearly 100,000 tons of hydrogen and helium that leak into the void, a process that once turned our neighbor Mars into a desert. The bottom line is a net loss of about 50,000 metric tons per year. It's a number that's huge to us, but meaningless on a planetary scale, posing no threat to our world's existence. Instead, this constant, invisible exchange paints a picture of our world as a dynamic, breathing entity, not a static rock. This dance of gain and loss is a fundamental part of the delicate balance that has allowed our world to remain a vibrant, living oasis in the vastness of space. It reminds us that even the most seemingly permanent things are in a constant state of change, and that our home is part of a much larger universe, full of forces both seen and unseen, all shaping our place in the cosmos. What if Earth weighed just 1% more? What if you woke up tomorrow feeling just a little heavier? Not because you skipped leg day, but because the Earth itself had packed on some pounds. Let's imagine our planet suddenly gained a seemingly tiny 1% more mass. You might not even notice at first, just a subtle, nagging drag on your body. But this small change is a ticking time bomb, an invisible countdown to a global catastrophe that will unravel our world in ways you can't even imagine. So, let's take a journey to this heavier Earth and see exactly how that bomb goes off, starting with the strange new feeling in your own body, and ending with the very planet cracking apart beneath your feet. You open your eyes. Something just feels off. It's a deep, bone-weary exhaustion you can't quite shake. As you push yourself out of bed, your feet hit the floor with a little more force than you remember. The simple act of standing takes a fraction more effort. Every part of you, from your bones to your blood, is now 1% heavier. If you weigh 180 pounds, you're now fighting an extra 8 pounds of force, 24/7. It doesn't sound like much, does it? But you can't put this weight down. It's fused into every cell in your body. This is your new normal. And while you're struggling to shake off this weird morning grogginess, the first domino in a planet-wide collapse has already fallen. You just don't know it yet. The personal scale. A heavier you. This new weight isn't like wearing a backpack. It's a fundamental rewrite of your biology. Deep inside your chest, your heart, a muscle that's been beating in a steady rhythm your whole life, is now working overtime, forever. It has to pump blood that's 1% heavier through thousands of miles of veins and arteries. This constant extra effort would almost certainly lead to a rise in baseline blood pressure for the whole population. Over months and years, the long-term strain could trigger a public health crisis, dramatically increasing the risk of heart disease for everyone on Earth. And it doesn't stop there. Take a deep breath. It's harder now, isn't it? The muscles in your chest have to fight more gravity just to expand your lungs. For a healthy person, it might just feel like a persistent, annoying shortness of breath. But for the millions of people with asthma or other respiratory illnesses, this extra effort could push them into a state of constant distress, overwhelming hospitals. Now, try to move. That morning jog you used to take? It now feels like running through ankle-deep mud. Every single stride is a struggle, and the force of impact on your knees and ankles is amplified. The careers of the world's greatest athletes would crumble overnight. Records would be frozen in time, relics of a lighter past. For the rest of us, it means a life of more fatigue and chronic pain as our joints wear down faster. A simple fall would carry a much higher risk of a broken bone. While our species might evolve denser bones over many generations, for the 8 billion of us here now, our skeletons just became dangerously fragile. Even standing upright becomes a battle. Your spine, a delicate stack of vertebrae, is under constant, increased compression. People would literally get shorter over their lifetimes. Back pain would become a global epidemic. For the elderly or anyone with mobility issues, just getting out of a chair could become a monumental task. Life, for everyone, has become more tiring and more painful. And while humanity is groaning under its own weight, the world around us is starting to break. The environmental shift. A crushing world. This change ripples out far beyond our bodies, rewriting the physics of our environment. Every object on Earth, from a single grain of sand to a whole mountain range, is now being pulled down with more force. This has immediate and startling consequences. Think of the forests. A giant sequoia that has stood for 3,000 years is suddenly holding up a weight it was never built for. Its massive branches are heavier, straining the trunk. Over time, new trees would likely adapt, growing shorter and stockier. But in the short term, we'd see a wave of structural failures. Massive branches would crack and fall, and some of the world's oldest and largest trees would simply collapse under their own mass. Animals would face a similar crisis. A condor, with its majestic wingspan, would struggle to get off the ground. Its body is heavier, and it needs more lift to fly. For many large birds, flight could become too difficult, or even impossible. Larger land animals would also suffer. An elephant would have to support hundreds of extra pounds of its own weight, putting immense strain on its legs and heart. Funnily enough, smaller creatures, especially insects, would fare much better. In this new world, the balance of power shifts, favoring the small and light over the large and majestic. The most dramatic changes, though, would happen to our water and air. Rivers would flow with more force, carving deeper into the land, causing more destructive floods, and washing away precious topsoil. Even raindrops would hit the ground harder, leading to a massive increase in soil erosion around the world, threatening our ability to grow food. And then there's the air. Our atmosphere, a huge ocean of gas held down by gravity, is now being squeezed, increasing the pressure all around us. This denser air is not only harder to breathe, but it also changes the weather. Storm systems could become more intense, as the denser air can hold and transport more energy. On top of that, a more compressed atmosphere would trap more heat, throwing our already fragile climate into further chaos and likely accelerating global warming in unpredictable ways. While we're still reeling from all of this, the world we built, the very foundation of our civilization, is starting to crumble. The collapse of a civilization. The unraveling. Our entire civilization is built on the quiet assumption that gravity never changes. Every bridge, every skyscraper, every dam, all of it. Engineers design buildings with safety margins, but those are for things like wind or snow, not for when the building itself suddenly gets heavier. Picture a suspension bridge. Its cables are perfectly calculated to support the dead load of the road deck. Now, that deck is 1% heavier. The cables are heavier. Every part is pulling down with more force. For older bridges, this new, permanent stress would be the final straw. We'd see a wave of catastrophic collapses across the globe, without any warning. Skyscrapers face the same terrifying problem. The columns at the base of a skyscraper are supporting the immense, cumulative weight of every floor above them. With everything now heavier, that load could become too much. It might not happen in a day, but microscopic stress fractures would begin to form. Over time, these buildings would become death traps. All new construction would grind to a halt. How can you build anything when the basic math no longer works? The crisis in the sky would be even faster. A plane flies because lift counteracts gravity. With every plane now 1% heavier, they'd need to fly faster to stay in the air, which means burning more fuel. For many planes, especially during takeoff, they operate at the very edge of their performance limits. That 1% could be the difference between getting into the air and stalling on the runway. Airlines would ground their fleets. Global travel and shipping would stop. The supply chains that feed our world would be severed. Food would rot, medicines wouldn't be delivered, and the global economy would spiral into a depression unlike anything in history. And what about getting to space? The speed needed to escape Earth's gravity would go up. It's not a huge jump, less than 0.5%, but our existing rockets, built with razor-thin margins, might not have the power to launch heavy satellites anymore. This would mean redesigning our entire space program, a costly and time-consuming setback that would cripple our global communication, navigation, and weather monitoring systems. As the lights go out, a deeper, more terrifying rumble begins from within the Earth itself. The planetary scale. A new Earth. This 1% isn't just a surface problem. It's a change to the entire planet, right down to the core. This extra mass creates an unimaginable pressure on the Earth's crust. Those massive tectonic plates floating on the mantle are already under incredible stress. Now, we've just cranked up the pressure on the whole system. The result would be a geological nightmare. Fault lines that have been quiet for thousands of years would awaken. We'd see an explosion of earthquakes on a scale humanity has never witnessed, leveling cities in an instant. This pressure would also squeeze the magma chambers beneath the world's volcanoes like a tube of toothpaste, triggering a dramatic increase in eruptions around the globe. Ash would choke our already compressed atmosphere, blocking out the sun and causing a volcanic winter. Some geologists have even speculated, and this is an extreme theory, that the crust couldn't handle the strain at all, potentially triggering a catastrophic planetary resurfacing. Meanwhile, the dance between the Earth and the Moon is thrown into chaos. Earth's stronger gravitational pull would tug the Moon into a slightly closer, faster orbit. This wouldn't create the planet-sized tsunamis you see in movies, but the results would still be devastating. Tides would become significantly higher and more powerful. Low-lying coastal cities that managed to survive the earthquakes would face chronic, catastrophic flooding every single day. And our trip around the sun. Ironically, that would barely change at all. The sun's gravity is so dominant that our little 1% gain is just a rounding error in the grand scheme of things. A cold comfort, really, for anyone left on a planet that's actively trying to shake itself apart. Long-term consequences and the new normal. If, by some miracle, anyone survived the initial cataclysms, the collapses, the quakes, the floods, what kind of world would they inherit? It would be a world reset to a pre-industrial age, but on a planet that's actively hostile to the life that came before. The long-term effects on our evolution would be profound. Fighting against higher gravity, the human form might adapt over thousands of generations. We could evolve to be shorter and stockier, with denser bones. Our hearts and lungs would need to be far more robust. Life itself would change. The age of giants, towering trees, and massive land animals would be over. The survivors would be living in the ruins of our world, looking up at a moon that appears just a little bit bigger in the sky, a constant reminder of the day the world changed, the day the Earth gained just 1%, and in doing so, lost everything that made it home. From a subtle feeling of heaviness to a planet tearing itself apart, the cascade of disaster is absolute. A change so small it seems insignificant unravels the very fabric of our existence. It's a powerful reminder of how miraculously fine-tuned our world is for us, how our bodies, our environment, and our civilization are all balanced on a gravitational knife's edge. The world as we know it isn't a given, it's a gift. One tiny nudge, and it all falls apart. What other seemingly small changes could have huge consequences? Let us know in the comments what if scenario you'd like us to explore next.